Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, let me know in the chats if I'm perfectly audible and visible to everyone. Quickly, I would want every one of you to let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Welcome back, guys. Welcome back. Welcome back. Welcome back. That's great. Welcome back. So, as you all must be knowing, till now, in this NEET Conquer batch, we are done with almost 5 chapters, right? We are done with the mole concept, redox reaction, states of matter, solid state, and chemical bonding, right? At the same time, HSP sir is done with general organic chemistry. At the same time, he is done with hydrocarbons as well. So, my dear students, today we'll be starting one of the most important chapters of your chemistry, one of the amazing chapters of your chemistry, one of the interesting chapters of your chemistry, and it's none other than your thermodynamics, right? This chapter is also considered to be the difficult chapter as far as NEET aspirants are concerned, right? But my dear students, you need not to worry. I'll be exactly starting from the basics. I'll be exactly starting from the scratch. Yeah? Perfect. So are you guys ready for the session? Quickly in the chats. Let me know quickly in the chats, people. Let me know quickly in the chats. Are you all ready for this particular thermodynamics chapter? Yeah? That's wonderful. At the same time, let me tell you whatever I'll be writing on the screen, I would want you guys to take a note of every single thing. Every single thing means every single thing, right? Whatever I'm going to write on the screen, you're supposed to take a note of everything. Anyways, at the end, I'll be sharing the handwritten PDF of this particular session in the Telegram group as well. I hope you all have already joined in there. Okay? So should we start the session? Yes or no? I need some thumbs ups in the chats. And I would want you guys to call up all your friends. Quickly. Quickly, people. Quickly in the chats. I would want you guys to let me know in the chats if all of you are super duper excited about this particular session. With the thumbs up. Let me see the Josh of the session first. That's great. Perfect, perfect, people. All right, then. Without wasting a lot of your time, let's get going. Let's get started, right? Everything is going to be completely handwritten today. Okay? It's going to be completely handwritten. So let's get going then. And let's start the chapter with the basic terminologies. The basic terminologies involved in the chapter thermodynamics. The basic terminologies which are involved in the chapter thermodynamics. Let's get to know about these basic terminologies first. Okay? My dear students, we have got 3 basic terminologies over here in the chapter. 3 basic terminologies. So first of all, I'll write the definition, then I'll make you understand what exactly it means also. Okay? Yeah? Let's have a look. Let's have a look. My dear students, the first terminology is what we call a system. The first terminology is what we call a system. The second terminology is what we call as surrounding. And the third terminology is what we call as boundary. Now, first of all, how do we define these terminologies? How do we exactly define these terminologies? Dear students, if you talk about the system is basically that part of the universe It is basically that part of the universe which is under thermodynamic, investigation. What exactly it means, you'll get the idea in some time. The second terminology, that is surrounding. How do we exactly define the term surrounding? Surrounding is, it is defined as the part of the universe except the system. Part of the universe except the system is what you call a surrounding. And how do we exactly define the boundary? I would say anything that separates system from the surroundings. Anything that separates system from the surroundings is what you call as boundary, or you can call it as wall as well. So these are three basic terminologies which you must know, right, in the beginning itself. So my dear students, let's get to know exactly what is the meaning of these basic terminologies. Have a look exactly what I'm going to talk about. Understand properly. My dear students, just to make you understand what is system, what is surrounding, and what is boundary, let me just do one simple thing. For example, I'm taking one container over here. Let's say this is the container which is closed on all the sides, right? This container is closed on all the sides. Now, dear students, what exactly I'm going to do? I'm going to keep water inside this particular container. Let's assume I have kept water in this particular container. Okay, so we have got H2O liquid inside this particular container. Let's assume that we have to do one thermodynamic investigation related to the water in the container. Let's say I have to do one thermodynamic investigation for this water which is there in the container. What kind of investigation? For example, I need to check how much heat is required to raise the temperature of this water by 1 degree. Let's say I need to increase the temperature of water by 1 degree. And I have to do one investigation that how much heat is required to raise the temperature of water by 1 degree. So in order to raise the temperature of water by 1 degree, I need to check how much heat has to be supplied, right? So can I say this water in the container right now is under thermodynamic investigation? Absolutely. Yeah. Sir, please put a live session on the channel. What is this going on then? Is this recorded? Can't you see there is live mentioned somewhere? Okay. So my dear students, this water in the container, it is right now under thermodynamic investigation. I'm doing a thermodynamic investigation related to water. I'm checking that how much heat has to be supplied to water in order to increase its temperature by 1 degree Celsius. So this particular water in the container is right now under thermodynamic investigation, and that part of the universe which will be under thermodynamic investigation, that is something which you call as system. So basically the water in the container right now is under investigation, so it is going to be your system. Okay, it is going to be your system. Number one. Number two, whatever is there in the universe except this water, except this system, whatever is there in the universe except this water, except this system, that is something which you will be calling as surrounding. That is something which you call as surrounding, right? Whatever is there in the universe except this water, except this system, right? That's something which I'll be calling as surrounding. Okay? And my dear students, as I told you, anything that separates system from the surroundings, that is something which you call as boundary. Do you see? The walls of the container, they are basically separating system from the surroundings. So I'll be calling this wall over here as boundary. Perfect. I hope these three terminologies are clear to you. That part of the system which is under thermodynamic investigation, that's something which you call a system. Any other thing in the universe except your system is what you call a surrounding. And anything that separates system from the surroundings, that's what you call as boundary. I hope this is super clear to everyone. right? Now, my dear students, understand few more things. Understand few more things. Now, you have got basically different types of boundaries which you have to remember basically. You have got different types of boundaries which I would want you all to remember. Number one. The first type of the boundary is what you call as a real boundary. Real boundary. One more is what you call as imaginary boundary. Then you have got diathermic boundary as well. And then you have got adiabatic boundary as well. You have got adiabatic boundary as well. Now, how do you define the real boundary? Real boundary is the one which you can see from your eyes. You can exactly see that there is something which is separating system from the surroundings. For example, this particular wall of the container, you can exactly see it, that it is separating system from the surroundings. And any such boundary which you can see by your eyes, right, which you can see by your eyes, that's what you call as a real boundary. Okay? Now, dear students, what is imaginary? Imaginary boundary cannot be seen. Cannot be seen by the eyes. It cannot be seen by the eyes. Let me make you understand what this imaginary boundary exactly is, right? How can you visualize it? For example, this is the container over here. Let's assume this is the container. This container is filled with water. This container is filled with liquid water. This is H2O liquid in the container. And this H2O liquid right now, it is under thermodynamic investigation, so it has to be in my system, right? This is the topmost layer of the water. This is the topmost layer of the water, right? My dear students, apart from this container, can I say there'll be atmosphere basically from outside? And what does atmosphere contain? Atmosphere contains different gases. So there'll be different gas molecules present in the surroundings. These are different gas molecules which are present in the surroundings, right? These are different gas molecules which are present in the surroundings. So this water in the container, that is your system. That is your system. And apart from that, what do we have? Apart from that, we have got surrounding as well. Apart from water, we have got surrounding as well. Now, my dear students, if I ask you one simple thing, do you see this part of the container? Do you see this part of the container is separating system from the surroundings? Yes, you can see it by your eyes. So this is your real boundary. It's your real boundary. Do you see this part of the container separating system from the surroundings? Yes. So again, it's your real boundary. Do you see this part of the container separating system from the surroundings? Absolutely. It's a real boundary. Okay. Now, my dear students, look at the topmost layer of water. Just above the topmost layer of water, what do we have? We have got atmospheric gases. Just above the top of the water, because I have kept container open on one side. Right? Can I say between the topmost layer of water and the atmospheric gases, between the topmost layer of water and the atmospheric gases, can I say one boundary will exist, one fine boundary will exist that will separate water from atmospheric gases? Can you see that boundary? You cannot see that boundary. But definitely there will be a fine line which will be separating atmospheric gases with water, which will be separating system from the surroundings. That boundary you cannot see by your eyes. And any such boundary which you cannot see by your eyes, that is something which you call as imaginary boundary. As simple as that. I hope this is clear. I hope this is clear, right? So I hope this particular scenario is clear to you, what this imaginary boundary is all about. Now, people, let's try to understand one more. Let's try to understand one more. What is that? That is diathermic boundary. What is diathermic boundary? Any boundary, any wall, any boundary, any wall, which allows the passage of heat, either from system to surroundings or from surrounding to system, right? Any boundary through which heat can pass. Any boundary which allows the passage of heat, either from surrounding to system or from system to surroundings. What do you call that boundary as? That's what you call as diathermic boundary, right? Which allows the passage of heat. Perfect. Now, my dear students, any such boundary which does not allow the passage of heat, either from system to surroundings or from surrounding to system, you'll be calling that boundary as diathermic boundary. Yeah, perfect. So, my dear students, a real boundary is the one which you can see by your eyes. Imaginary boundary cannot be seen by the eyes. Diathermic boundary allows the passage of heat either from system to surroundings or from surrounding to system. And at the same time, your adiabatic boundary, it does not allow the passage of heat either from system to surroundings or from surrounding to system. Right? Perfect. I hope this is clear to you. It's again complete basics. Moving on to different types of systems. How many different types of systems do we have? How many different types of systems do we have? My dear students, the first type of the system is what you call as open system. Open system is the first type. Second is a closed system. And the third is, that is isolated system. Open system, closed system, isolated system. Right? What exactly this open system does? What exactly this open system does? Let me tell you, open system, it allows the exchange of energy. It allows the exchange of energy as well as matter. Open system allows the exchange of energy as well as matter. With what? With the surroundings. With the surroundings. Whereas closed system, it only allows the exchange of energy with the surroundings. It only allows the exchange of energy with the surroundings. Whereas if I talk about the isolated system, it neither allows the exchange of energy nor it allows the exchange of matter with the surroundings. Right? Very simple and basic. For example, just to make you understand. Let's say this is the container which you have taken. The container is open on one side. I'm keeping liquid water inside this container. This is liquid water inside the container. This is your H2O liquid, right? Let's assume that the walls over here are diathermic. If the walls are diathermic, they will allow the passage of heat. Now, my dear students, for example, this water is my system right now. It is under thermodynamic investigation. Okay? What exactly I'm doing? I'm supplying some heat to this water. When I supply heat to the water, after some time, what is going to happen? Can I say evaporation will start? The water will start getting evaporated and those vapors will go into the atmosphere, right? What is heat basically? The heat which I'm supplying. What is heat? Heat is the mode of transfer of energy basically, right? Can I say this particular system is exchanging energy as well as matter with the surroundings, right? As you can see, energy is coming from surrounding to the system and matter is going from system to surroundings. So this is one clear-cut example of what? Open system. It allows the exchange of energy as well as matter with the surroundings. Yeah? Perfect. At the same time, any such system which allows only the exchange of energy with the surroundings. Just to make you understand, for example, if I close this container, when I close this container, will there be any exchange of matter between system and surroundings? There will be no exchange of matter with the surroundings. Then I'll be calling this particular system as closed system. And any such system which neither allows the exchange of energy nor the matter with the surroundings, that's what you call as isolated system. Right? That's what you call as isolated system. What is the example of isolated system? If you consider entire universe as your system, if you consider entire universe as the system, if you take entire universe into investigation, right? That becomes the perfect example of what? That becomes the perfect example of isolated system, right? So open system, it allows the exchange of energy as well as matter with the surroundings. Closed system, it only allows the exchange of energy with the surroundings, not the matter. And isolated system, it neither allows the exchange of energy nor the matter with the surroundings. I hope it is super clear to you. Yeah? Now, my dear students, let's get to know about some important things now, right? Let's get to know about some important things now. There is something called as extensive property. There is something called as extensive properties. Extensive properties and intensive properties. Now, what these extensive and intensive properties are all about? What these extensive and intensive properties are all about? I'm straight away going to write the definition of extensive properties. Then I'll make you understand what they exactly mean, right? This is something which is important. Okay, understand. Extensive properties, let me tell you, these are the properties of system, basically. These are the properties of system whose value changes on changing the size of the system. Whose value changes, or let me write it like this. These are the properties of the system whose value changes on changing the amount of substance. Whose value changes on changing the amount of substance present in the system. Present in the system. Right? And over here, I'm writing otherwise intensive. Otherwise intensive. Now let's get to know exactly what it means. Try to understand it carefully. Okay? Try to understand carefully. Okay, have a look, guys. So for example, imagine that you have got an object. Let's say this is one object. This is one block. This is one block of iron, right? This is an object, block of iron. For example, this iron block is right now under investigation. So this complete iron block is my system right now. This complete iron block is my system right now. Let's assume that the mass of this whole system is capital M, its volume is V, and its temperature is T. Let me assume that. The mass of this whole system, the mass of this block, it's M, volume is V, temperature is T, right? Now, dear students, if I just do one thing, if I divide the block into two parts, I divided the block into two equal parts, right? Now I'm taking only this part. So this part of the block is now under investigation. Can you let me know what is going to be the mass of this part of the block now? Is it going to be M or M by 2? It's going to be M by 2. Is its volume going to be V or V by 2? It's going to be V by 2. Is its temperature going to be T or T by 2? Its temperature will remain T only, right? Temperature won't change. So my dear students, first this whole block was under investigation. Now only half of the block is under investigation. You tell me, am I changing the size of the system? Absolutely, I'm changing the size of the system. And when I'm changing the size of the system, is the mass of the system changing? Mass of the system is changing from M to M by 2. Volume of the system is also changing from V to V by 2. But temperature of the system is not changing. Any such property whose value changes on changing the size of the system, any such property whose value changes on changing the amount of substance present in the system, you'll be calling that property as extensive property. So initially I defined three properties here. And out of three properties, two properties we have which are changing their values on changing the size of the system, right? So out of three properties, two properties are going to be extensive, right? two properties are going to be extensive. Whereas one property, which is temperature, it's not changing on changing the size. So temperature is going to be the example of intensive property. Is it clear? Is this part clear to everyone? Temperature is your intensive property. Right? And my dear students, there are a lot of examples which you need to remember about extensive and intensive properties, which we'll discuss also in this chapter only, but not now. But not now, right? Because we have to understand those terminologies in the chapter first, then only you can get to know why those properties are extensive and intensive. So right now, I would want you guys to just take a note of these properties. So first of all, the examples of extensive properties. Examples of extensive properties. Now you tell me, what are the examples of extensive properties? First of all, mass is going to be extensive. Volume is going to be extensive. Number of moles of a substance, it's going to be extensive. There's a term which we have to discuss in some time, that's heat capacity. Heat capacity is extensive, right? There's a term which we have to discuss in some time, internal energy. Internal energy is extensive. Enthalpy. Enthalpy is extensive. Entropy. Entropy is extensive. Gibbs free energy. It's again extensive. These are some very important properties which you have to remember, right? These are the examples of what? Extensive properties. Now, you must be thinking, what are the examples of intensive properties? There are many examples of intensive properties as well. There's students, temperature. Temperature. It is the perfect example of intensive property. Number one. Number two, density of a substance. Density of the substance is the perfect example of intensive property, right? Pressure of the gas. It is the perfect example of intensive property. There is something called as specific heat capacity. There is something called as specific heat capacity. It is again one example of intensive property. There is something called as molar heat capacity. There is something called as molar heat capacity. Again, one of the example of intensive property. There is something called as molar volume. Molar volume, intensive property. Molar entropy. Molar entropy, intensive property, right? Concentration, intensive property. pH, intensive property. Boiling point, intensive property. EMF, intensive property. These are all the examples of basically intensive properties. My dear students, I would want all of you to remember these intensive properties. Because question is asked, which of the following is extensive and which of the following is intensive? Perfect. You'll be given with 4 options. You have to select one. Yeah? Perfectly done. Now, there are some important features of these extensive and intensive properties. Some very, very, very important features. Number one. The first important feature of extensive property. My dear students, when we talk about the extensive properties, let me tell you, extensive properties are additive in nature. They are additive in nature. What does that mean? That means the extensive properties, they can be added or subtracted directly. Intensive properties cannot be added or subtracted directly. So I'll say intensive properties are non-additive. Now, what exactly it means? Have a look. For example, this is one container which I took. Okay. This is one more container which I took. Right. And this is one more container which I took over here. Yeah. Simple. I'm taking 3 containers. This container is, for example, filled with water. There is water inside the container. This container is also filled with water. It is also filled with water. Let me assume mass of this water is m, its volume is v, and its temperature is T. Let me assume mass of this water is m, its volume is v, its temperature is T. Perfect. Now, my dear students, this container contains water. Even this container contains water. If I pour the water inside both the containers into this final container, this final container will be completely filled with water, right? I'm pouring the water in both the containers into this final container. Now tell me, what is the mass of the water present in the final container? It's going to be 2m. Volume of water over is going to be 2v, but its temperature will remain as such. It's going to be T only. Yeah, it's going to remain T only. So first of all, how many properties of system did I define? I defined 3 properties: mass, volume, temperature. I defined 3 properties: mass, volume, temperature. Out of these 3 properties, how many are extensive? This is extensive, this is extensive, whereas temperature is intensive. My dear students, do you see, when we are pouring the water in both the containers in this final container, what is happening to mass? Mass of this water was m, this was m, so m plus m makes it 2m, right? Similarly, my dear students, v plus v, it makes it 2v, correct? T plus T, it is not making it as 2T. It is not making it as 2T, right? So my dear students, we had 2 extensive properties, and extensive properties are directly being added. Extensive properties are directly being added. Whereas, do you see intensive properties being added? No. If intensive properties were added to, then over here temperature should have been 2 times T. But that's not the case. That's not the case, right? Someone is saying, why not 2T? Let's say I have a glass filled with water. Its temperature is 25 degrees centigrade. One more glass filled with water. Its temperature is also 25 degrees centigrade. Pour them into a tub. What will be the temperature of the final water? Is it going to be 50 degrees centigrade? Are you saying something like that? Yeah. So you can see, out of these 3 properties, 2 were extensive. And extensive properties are straight away being added, whereas intensive properties are not. This is one important statement. Because from this particular statement, a particular type of question is asked in electrochemistry chapter, which is most probably going to be our next chapter, right? I cannot show that right now. I'll show it in electrochemistry. Perfect. So remember this. Extensive properties are additive, whereas intensive properties are non-additive in nature. Now, my dear students, one more important thing. Let me tell you division of 2 extensive properties. Division of 2 extensive properties makes the new property as intensive. Makes the new property as intensive. What does that mean? Have a look. For example, I have got the object whose mass is m. Right? Volume of the same object is V. I've taken an object whose mass is m, whose volume is V. Now tell me whether mass is extensive or intensive. This is extensive. Volume, it is extensive. If I divide the two, mass by volume, it will be density. And density is the example of what? Density is the example of intensive property. So basically, when you divide 2 extensive properties, the new property that comes into play, that new property will be intensive in nature. Simple. Yeah. Is this clear to everyone quickly in the chats? At the same time, there is one more important thing. Okay, let me summarize it. So it is extensive property divided by extensive property. It makes the new property as intensive. This is something which you have to remember. Extensive by extensive is intensive. Yeah? Extensive by extensive is basically intensive, right? So this was the second feature. This was basically the second feature of your extensive property. Now, my dear students, talking about the third important feature. What is that? Have a look. I'm writing a statement. When an extensive property is expressed, per unit mass, comma, per unit mole, or per unit volume, the new property becomes intensive. Now, what that exactly means? Have a look. There is a term basically which we have to discuss in some time. That's called as heat capacity, which is represented by C. Let me tell you, heat capacity represented by C It is one of the example of extensive property. Yeah. Now, my dear students, if I define heat capacity per unit mass, heat capacity per unit mass, this is now called as specific heat capacity. This is now called as specific heat capacity. Specific heat capacity. Again, this is something which we have to discuss in some time. And let me tell you, the specific heat capacity, it is the example of intensive property. So, when an extensive property is expressed per unit mass or per unit mole, for example, C divided by N, heat capacity per unit mole is called as molar heat capacity. It is called as molar heat capacity, right? It's called as molar heat capacity. Since heat capacity was extensive in nature, therefore molar heat capacity will be intensive in nature, right? Simple and basics. Yeah. Similarly, my dear students, there are other things as well. For example, V stands for volume. V stands for volume. If I divide it with number of moles per unit mole, V by N is something which we call as molar volume. Volume was the example of extensive and molar volume will be the example of intensive. For example, you have got entropy, S, which is the example of extensive. Per unit mole, it is called as molar entropy. Molar entropy is the example of intensive property. So do remember these particular things as well. Whenever an extensive property is expressed per unit mass, per unit mole, or per unit volume, the new property becomes intensive, right? So quickly, give me some thumbs ups in the chats if you got this particular concept properly. Quickly. Quickly, people. Let me know in the chats quickly if all the things are clear till here. Someone is asking, sir, please do previous year questions as well. In every session, we do PYQs as well. You need not to worry about that. I exactly know what to do and what not to do. Okay? You just follow what I'm teaching. Nothing else. Yeah? I hope these three statements are clear regarding extensive and intensive properties. Now, my dear students, there is one more thing. Just a second. There is one more important thing. And what is that important thing? Let's have a look. Just a second. Let me add up some blank slides so that it will be easy to understand, basically. All right, let's move on. My dear students, there is something called as state parameters. State parameters. How do you exactly define these state parameters? Let me tell you. State parameters are basically, these are the variables. These are the variables which actually defines the state of the system. These are the variables which actually defines the state of the system. For example, pressure, volume, moles, temperature. These are the variables basically which actually defines the state of the system. Number one. Number two, in order to change the state of the system, the value of state parameters needs to be changed. The value of state parameters needs to be changed. If you want to change the state of the system, you will have to change the value of state parameter. Right? And my dear students, if you change one of the state parameter of the system, the state of the system will automatically change. Minimum In order to change the state of the system, minimum you have to change one state parameter. Maximum you can change many. Yeah? Right? Yes, Divya, this is absolutely free. All the sessions are happening on YouTube only. Absolutely, it's for 2024, even 2025 students can also watch it. Yeah? Okay. So my dear students, let me just make you understand this particular statement. Understand. For example, this is the container. And for example, I have got an ideal gas inside this container. These are the ideal gas molecules which are present inside the container. This ideal gas right now is my system. I'm assuming the pressure of this gas is P1, volume of this gas is V1, temperature of this gas is T1, moles of this gas are N1, right? So I can categorically say when the pressure of the gas is P1, when the volume of the gas is V1, temperature T1, moles N1, I can say the gas is present at its initial state. I can say the gas is present at its initial state. So these are basically the parameters, these are the variables which actually define the state of the system. They actually define the state of the system. And people, at the same time, if you want to change the state of the system, you have to change the value of state parameters. Minimum you can change one state parameter, maximum you can change many, right? For example, I'm changing the pressure of the gas. Let's say I'm changing the pressure of the gas from P1 to P2. Volume I'm changing from V1 to V2. Moles I'm changing from N1 to N2. Temperature I'm changing from N1 to T1 to T2. So I think I changed all the state parameters. And when you change the state parameters, what happens to the state? State of the system automatically changes. Now, you cannot say that this system, you cannot say that this gas, you cannot say it's present at initial state now. Let's call this as the final state. This is going to be the final state of the gas. So in short, what I want to convey at this particular point of time. Yes, Monish, you can do that. What I want to convey over here, what is that? When you want to change the state of the system, you will have to change the value of state parameters. Minimum, if you change one state parameter, the state of the system automatically will change. As simple as that. Yeah, as simple as that. And what are these state parameters? These are basically some variables which actually defines the state of the system. Through these variables only you get to know where the system, through these variables only you get to know that whether the system is present at its initial state, at its final state, at the intermediate state, or wherever. Yeah, through these state parameters. This is again one basic thing which you need to know. I hope this is clear. My dear students, there is something called as state function and path function. There is something called as state function and path function. State function and path function. What are state functions and what are path functions? Let me write their definition and some important points so that there won't be any doubt afterwards. Okay? My dear students, state functions are the ones whose value depends only on the initial and the final state of the system. State functions are the ones whose value only depends on the initial and final state of the system. Let me tell you these state functions, these are path independent. These are path independent. Well, if the value of a state function only depends on the initial and final state, what do we do then? Therefore, we calculate change in the value of state function. And change in the value of state function is always equal to the final value of state function minus the initial value of state function. Final value of state function minus the initial value of state function. What are the examples of state functions? There are basically a lot of examples, which we are going to discuss in some time. Internal energy, that is the example of state function. Enthalpy, state function. Entropy, state function. Gibbs free energy, state function. Right? Right, people? So, I can say the examples of state functions are internal energy. That's why I'm calculating change in it. Enthalpy, delta H. That's why I'm calculating change in it. Gibbs free energy. delta G, entropy, delta S, right? These are the common examples of what? These are the common examples of state functions basically. Now guys, there is one important point which I would want you guys to remember from now onwards. What is that? For example, A is a state function. A is a state function. A is a state function, for example. Acha, do you remember one thing? Have you studied distance and displacement? Displacement only depends on initial and final. Distance is path dependent. Displacement is not path dependent. Right? Whenever you get confused with state functions or path functions, you can relate it with distance displacement so that you can memorize it properly. Yeah? Perfect. Now people, for example, A is a state function. This A can be internal energy, this A can be enthalpy, it can be Gibbs free energy, it can be entropy, right? Now my dear students, if I multiply this A by D, if I write dA, what this dA indicates? It indicates small change in A. It indicates small change in A, right? It indicates small change in A. Now, if I integrate this dA, what is dA? Small change. You're integrating it. Now it becomes large change. Now it gives you the large change, or you can say the total change. Large change in A. This is one simple thing which I would want you guys to remember. One simple thing which I would want you guys to remember. For example, U stands for internal energy. U stands for internal energy, right? U stands for internal energy. My dear students, if I ask you whether the internal energy is the example of state function or path function, it is the example of state function. It is the example of state function. Dear students, if you multiply this internal energy by D, it becomes du. Now, how should I pronounce this du? What should I call this du? This du is going to be small change in internal energy. I'll be calling this as small change in internal energy. Now, if I integrate this small change, it gives me the large change in internal energy. It gives me the large change, or you can say the total change. The large change or total change in internal energy. This is one more important point which I would want every one of you to remember. Right? Perfecto. Now, my dear students, one more thing. Since these were state functions, that's all. That's all. Nothing else to remember about it. Okay? Nothing else to remember about it. Now, guys, there is something called as path function. There is something called as path function. How do you exactly define the path functions? Let me tell you, these path functions, they also depend upon the initial and final state. They also depend upon initial and final state. They also depend upon the initial and final state. And apart from that, they are path dependent as well. They are path dependent as well. What are the common examples of path functions? It's going to be heat and work. Heat and work, these are basically the common examples of the path functions. Why they are the path functions? You'll get the idea when I'll teach you the PV work, area under PV curve, right? Afterwards, there only you'll understand exactly how come this work and heat, they exactly are the path function, right? Their value depends on initial state, final state. Apart from that, they'll be path dependent. They're path dependent functions. And my dear students, whenever you get confused with state or path functions, just try to relate it with distance, displacement. Displacement, initial, final state. Distance, initial, final state, and path dependent. Try to relate it with it. Yeah? Okay? Now guys, there is one more thing. This heat is represented by Q and work is represented by W. This is something you must remember from now onwards. Point number one. And point number two. Point number two. My dear students, for example, A is a path function. For example, A is a path function. This A can be heat, it can be work. Okay, for example, A is a path function. If I multiply this A by D, it becomes dA. dA, I won't be calling it as small change in A. No, dA is a path function. I'll be calling it as small amount of A. I'll be calling it as small amount of A. And if I integrate it, if I integrate it, small amount integration, I won't represent it with delta A. I'll just represent it with A. And A denotes large amount or total amount of it. For example, what is Q? Q is heat. Heat is the example of path function. If I multiply dQ, since Q is the path function, heat is the path function, so I won't be calling this dQ as small change in heat. Does not make any significance. This I'll be calling a small amount of heat. This I'll be calling a small amount of heat. And my dear students, if I integrate it, it becomes Q. It becomes Q, which represents total amount of heat. It represents total amount of heat. I hope you guys are going to remember all these things. Yeah? Perfect. Is it clear till here? Say yes or no in the chats quickly. All these things should be clear till here, I believe. I believe all these things should be clear till here. Yeah? Okay. Now, my dear students, till now we were only talking about the basics. I'm just giving you the idea about different things which we have to discuss in the chapter. Okay? I'm just giving you the idea of the things. Later on, we'll be discussing about all these things in detail. Heat, work, internal energy, enthalpy, Gibbs free energy, everything. Right? Now understand what I'm going to do. There is something called as thermodynamic process. I'm right now just going to give you the idea about thermodynamic process. I'm not going to teach you in detail right now. In detail, we'll discuss it after some time. I'm just giving you the idea what thermodynamic process is all about. What thermodynamic process is all about. My dear students, if you want to define the thermodynamic process, it is basically defined as the path followed. It is defined as the path followed to change. The path followed to change the state of the system. Path followed to change the state of the system. Now you must be thinking what it means. Path followed to change the state of the system. What does that mean? Try to understand this. For example, you have got an ideal gas in the container. Let's say these are the ideal gas molecules which are present in the container. Right? These are the ideal gas molecules. And this ideal gas is my system right now. It is under thermodynamic investigation. Right? Let's assume the pressure of the gas is P1, volume is V1, temperature is T1, moles are N1. For example. And I'm assuming when the pressure is P1, volume V1, temperature T1, moles N1. I'm assuming that the gas is present at its initial state. So right now, this gas is present at its initial state. Correct? Now guys, as I told you a few minutes back, if you want to change the state of the system, what you exactly need to do? In order to change the state of the system, we need to change the value of state parameters, right? We need to change the value of state parameters. Minimum, if you change one state parameter, the state of the system will automatically change, right? For example, I'm going to change the value of state parameters of this gas. I'm going to change the value of state parameters of this gas. For example, the number of moles present in the container initially were N1. Now, for example, the number of moles are N2. Let's say the temperature of this gas now is T2. Volume is V2. But pressure, I'm keeping the same, P1. Have I changed the state parameters? Yes, I have changed the state parameters. When you change the state parameters, the state of the system automatically changes. Let me call this as the final state of the system. Let me call this as the final state of the system. My dear students, if you analyze one simple thing, did I change the state of the system? Yes, I changed the state of the system. But the pressure of the gas initially was P1, finally also it's P1. What does that mean? That means I changed the state of the system without changing the pressure of the gas. I changed the state of the system without changing the pressure of the gas. right? I made sure that the state of the system changes without changing the pressure of the gas. So what I did exactly, I kept the pressure of the gas constant. I kept the pressure of the gas constant. Since I changed, no doubt, I changed the state of the system. But when I was changing the state of the system, I made sure that pressure of the system should not change. My dear students, can I say, I could have changed the state of the system by keeping the volume of the system constant as well. I could have changed the state of the system by keeping temperature of the system constant as well, right? So can I say, I have got many paths available. I have got many paths available to change the state of the system. I can change the state of the system by keeping the pressure of the system constant. I can change the state of the system by keeping the volume of the system constant. I can change the state of the system by keeping the temperature of the system constant. So I have got many paths available, right, to change the state of the system. And the path followed out of these paths, that path which you are following, the path followed to change the state of the system, that's something which you call as thermodynamic process. So what is thermodynamic process? It is the path followed to change the state of the system. You have got different paths available to change the state of the system. Now, out of those paths, which path you are following to change the state, that defines the thermodynamic process, right? Now, dear students, understand. The first thermodynamic process whose idea I'm giving you, that's isochoric process. In isochoric process, what happens? In isochoric process, you will be changing the state of the system by keeping the volume of the system constant. You won't let the volume of the system change while changing the state of the system. Right? Number one. Number two, if volume of the system is constant, change in volume, which is V final minus V initial, that has to be zero. Change in volume has to be zero, right? And my dear students, if you just want to plot a graph, or leave graph aside, tell me one thing. Have you studied gas laws? Right? In which gas law, volume of the gas is kept constant? In which gas law, volume of the gas is kept constant? You call that gas law as Gay-Lussac's law. I'm changing the state of the gas by keeping the volume of the gas constant. So can I say, the gas which is under investigation right now, that will be straight away following the Gay-Lussac's law? That will be following the Gay-Lussac's law. And as far as the Gay-Lussac's law is concerned, P1 divided by P2 has to be equal to P1 divided by T2. So whenever you'll be having an ideal gas undergoing isochoric process, that ideal gas will be following this particular equation, right? That will be following this particular equation. At the same time, if I ask you, plot the graph between pressure and volume. Since you are keeping volume constant, so volume is not supposed to change. Volume you have to keep constant. So it has to be a straight line, right? It has to be a straight line. And you call this graph as isochore. I hope this is clear to everyone. I'm just giving you the idea of the things. I'm not teaching in detail right now. I'm just giving you the idea. All these processes we have to discuss in detail afterwards. Okay? Perfect. So number one was your isochoric process. Now similarly, you have got isobaric process as well. Tell me what happens in isobaric process. When do we say that the gas is undergoing isobaric process? When can we say that the ideal gas is undergoing isobaric process? First of all, let me tell you one thing. Med talks, I did not talk about work yet. I'm not involving work right now. We have to discuss that as well. Just try to understand what I'm telling. That's it. Okay, we'll go to work as well. Just wait. Okay. So let me just remind you one thing. From now onwards, whenever I talk about ideal gas, whenever I talk about system, whenever I say that I have got a system with me, understand that I have taken an ideal gas in the container and that ideal gas is under investigation. Because in this chapter, we have to deal with only the thermodynamics of ideal gases. Perfect. So from now onwards, whenever I'll be using the term system, understand that we have got a container which contains the ideal gas and that ideal gas is under thermodynamic investigation, right? Now, my dear students, when do we say that the ideal gas, that the system is undergoing isobaric process? If during the change in the state of the system, if during the change in the state of the gas, pressure of the gas does not change at all. Pressure of the gas does not change at all. You're changing the state of the gas. You're changing the state of the system. But during the change in the state of the system, pressure is not changing. You'll be calling that process isobaric process. You can say that the gas is undergoing isobaric process. Right? So my dear students, what will be change in pressure? Change in pressure absolutely zero. Now, if you remember in states of matter, which gas law we introduce at constant pressure? It is Charles' law, which is used at constant pressure. So my dear students, Charles' law equation used to be like this: V1 divided by V2 is equal T1 divided by T2. So whenever the ideal gas undergoes isobaric process, you can use this particular equation for the ideal gas. Yeah, right? And by chance, if you want to plot a graph between pressure and volume, how the graph looks like? Pressure you have to keep constant. You'll be calling this curve as isobar. I hope this is again clear to everyone. Now, my dear students, one more thing. There is something called as isothermal process. What happens in isothermal process? When do we say that the ideal gas is undergoing isothermal process? My dear students, if you will be changing the state of the gas, if you will be changing the state of the system without doing anything to its temperature, without letting its temperature to change, that means you are changing the state of the gas by keeping the temperature of the gas constant, then only I can say that the system is undergoing isothermal process, right? So change in temperature over here has to be zero, right? In which gas law temperature is kept constant? That's Boyle's law. So when the gas undergoes isothermal process, it has to follow the Boyle's law. And what was the basic equation of Boyle's law? P1V1 is equal to P2V2. So when the ideal gas undergoes isothermal process, it will be following this equation, right? And my dear students, or you can say something like this. You can say P is equal to K by V. This is the equation as far as the Boyle's law, right? And if you want to plot the graph between pressure and volume, can you let me know what will be the nature of the graph? Pressure and volume, they are inversely proportional to each other. So the nature of the curve has to be a rectangular hyperbola. And you call this particular curve as isotherm. Right? Whenever you need to plot a curve between two variables which are inversely proportional to each other, the nature of the curve has to be rectangular hyperbola. So this curve is rectangular hyperbola and you will be calling it as the isotherm. Yeah? Correct? And my dear students, this particular equation, you call this as the equation of state. This is called as equation of state for isothermal processes. Equation of state for isothermal processes. Right? Now, similarly, there is one more thermodynamic process which we have to discuss in detail. But right now, I'm just giving the idea of the things. Right? I'm not teaching these processes in detail now. Giving you just the idea of the things. Right? All these processes we have to discuss in detail. I'm writing adiabatic process. When do we say that the system is undergoing adiabatic process? if there will be no heat exchange, between the system and surroundings during the change in the state of the system. So basically, Q value has to be 0. So whenever the system undergoes a change in state, whenever you will be changing the state of the system, but you will make sure during the change in the state, there should be no heat exchange. There should be no heat exchange between the system and surroundings. Heat should not enter into the system or should not leave the system, right? Then only I can say that the system is undergoing adiabatic process. My dear students, I told you the equation of state for isothermal process. Similarly, there is one more equation of state here. That is PV raised power gamma is equal to constant, right? This is the equation of state. This is what you call as equation of state for a reversible adiabatic process. What is reversible? You will get the idea in some time. Okay, this is something which you call as a reversible adiabatic equation of state for reversible adiabatic process, right? There are basically two types of adiabatic processes: reversible adiabatic, irreversible. I'll discuss about that afterwards. Okay. Now, first of all, you can write the same equation in this format: P is equal to K divided by V raised power gamma. Absolutely. Now tell me whether pressure and volume, they are directly proportional or inversely. They are again inversely proportional. If they are inversely proportional to each other, tell me the nature of the curve. This has to be again the hyperbola. They are inversely proportional. The nature of the curve is hyperbola, right? And you'll be calling it as adiabat. You'll be calling this curve as adiabat. Now you tell me one thing. In case of isothermal process, PV graph was hyperbola, right? And in case of adiabatic process also, PV graph is hyperbola. Now, how can you distinguish between two hyperbolas, whether it's for adiabatic or isothermal? How do you do that? Let me tell you one simple trick, right? Or let me write the concept first of all. I'm not going to derive the concept because that's of no use to you. Just remember it. And later on, like after 1-2 minutes, I'll be giving you one trick as well. That trick is important, right? Leave the trick aside right now. Let me write the concept. Do remember slope of the tangent. Slope of the tangent at a point. On PV curve for adiabatic process. Is equal to gamma times the slope of tangent at a point on PV curve for isothermal process. And do remember one more thing: gamma, that's something which you call as Poisson's ratio. We'll be discussing that also in some time. Do remember its value is always greater than 1. If gamma value is greater than 1, can I say the slope of adiabatic in general will be greater than that of slope of isotherm, right? If you do not want to remember this, then do remember one simple trick. See guys, for example, this is pressure and this is volume, right? I'm going to draw two hyperbolas. This is one hyperbola. This is one more hyperbola, for example. I'm putting the arrow on the right. I'm putting the arrow on the right. Now tell me, towards right, whether the volume is increasing or decreasing. Towards right, the volume is increasing. Increase in the volume is something which you call as expansion. So basically, both these graphs, they represent expansion. They represent expansion, right? How do you justify, leave the justification aside. How do you differentiate which curve is isotherm and which curve is adiabat? What you need to do exactly is just one simple thing. Select the common point. This is the common point, right? Place your thumb at the common point. Curl your fingers in the clockwise direction. That curve which touches the fingers first, that has to be your isotherm always. The other one is going to be adiabat. The other one automatically is going to be adiabat. As simple as, right? For example, you have got two graphs like this. This is pressure and this is volume, right? Let's say I'm starting from this point. And I'm making two hyperbolas like this. These are the two hyperbolas which I made. I'm keeping the arrow towards left. Tell me first of all, towards left, whether volume is increasing or decreasing. Towards left, volume is decreasing. Decrease in the volume is something which we call as compression. Decrease in the volume is something which we call as compression, right? Now, tell me which one is isotherm, which one is adiabat. Again, do same thing. Place your thumb at the common point. Curl your fingers in the clockwise direction. That curve which touches the fingers first, that has to be your isotherm. So this is going to be your isotherm, and the other one automatically, that is your adiabat. I hope this is clear. Yeah, very simple and basic. You are going to remember it like this from now onwards. Yeah, quickly let me know in the chats with the thumbs ups. Sir, would you teach atomic structure? Surely, why not? I'll teach everything, chill. Quickly, guys, let me know in the chats with the thumbs ups if all the things are clear till here. Yeah? I'm not teaching these processes in detail now. I'm just giving you the idea of some basic things. I did not teach them yet. Okay? Just keep that thing in mind. I did not teach them in detail yet. This is just the basic introduction of the thing. Perfecto. Moving ahead, guys. There is something called a cyclic process. I'm just giving you the definition of it. Cyclic process. When do we say that the system is undergoing cyclic process? When do we say that the gas is undergoing a cyclic process? How do we define the cyclic process? In cyclic process, what happens basically? System returns to its initial state. System returns to its initial state after going through a lot of steps. After going through a lot of steps. This is again one very important topic which we have to discuss in detail. There are a lot of questions which are based on this. Yeah, a lot of questions which are based on this. But I'm just giving you the idea of the things, right? I'm not teaching it. I'm just giving the idea. Cyclic process. In cyclic process, what happens? System returns to its initial state. Let me give you an analogy. One analogy is enough. For example, you're starting from this point. You're starting from this point. This is your initial state, for example. You're going from point A to point B. Then you are going from point B to point C. Then from C, you're going again to A. You're going again to A, right? Can I say your initial state and final state is same? Can I say your initial state and final state is same? And my dear students, whenever system returns to its initial state after going through a lot of steps, what do we call this process? Cyclic process, right? So I can say the system is undergoing cyclic process, right? The system is undergoing cyclic process, right? One simple thing. Is the initial and final state of the system same? Absolutely. if the initial and final state of the system is same, can I say the initial value of state function and final value of state function will also be same? Because state function only depends on initial and final state. State function changes. State function only depends on initial and final state. If the initial and final state is same, so the final value of state function will be equal to the initial value of state function. And change in the value of state function will be equal to final value of state function minus initial value of state function. That has to be 0. Right? That has to be 0. Perfect. So for a cyclic process, delta U value will be U, internal energy. Internal energy is a state function. Change in the value of state function for a cyclic process, that is 0. So delta U for the cyclic process is 0. Delta H for a cyclic process is 0. Why? Because enthalpy is a state function. Entropy change for the cyclic process, that has to be 0. Gibbs free energy for the cyclic process, that has to be 0. All these things, again, we have to discuss in detail only. Right now, just the basic idea I'm giving. Right? So change in the value of state function for a cyclic process, that is absolutely going to be 0. Is this clear? Is this clear to you? Is this clear to you, people? Yeah? Now, there is something called as heat, which is represented by Q. There is something called as heat represented by Q. Right? What is heat exactly? What is heat? Can you define heat? My dear students, heat, when we talk about heat in particular, heat is defined as the mode of transfer of energy. It is defined as the mode of transfer of energy between the system and surroundings. Mode of transfer of energy between system and surroundings. Whenever exchange of energy has to take place between system and surroundings. Whenever exchange of energy has to take place between system and surroundings. The exchange of energy between system and surroundings. The transfer of energy between system and surroundings can be done via heat. So what is heat? It is just the mode of transfer of energy between system and surroundings. For example, if energy is to be sent from system to surroundings, or if the energy is to be sent from surrounding to system, this transfer of energy, this exchange of energy between system and surroundings can be done via heat. So heat is just the mode of transfer of energy between system and surroundings. Right? Why does heat flow? Why does heat flow? You know it, heat flows due to temperature difference. Heat flows due to temperature difference. And heat always flows from higher temperature to lower temperature. It always flows from higher temperature to lower temperature. For example, this is the container which we have. Let's say this is the container which we have. And in this container, what do I have? I've got gas. The gas is my system. Right? T system represents the temperature of system. And outside the system, there is surrounding. And T surrounding represent the temperature of surroundings. Temperature of system is represented by T system. Temperature of surrounding is represented by T surrounding. Right? One thing. If, for example, if T surrounding is greater than T system, if the temperature of surrounding is more than that of temperature of system, can I say there will be temperature difference between system surroundings? And whenever there is temperature difference, heat automatically flows from higher temperature to lower temperature. Right now, surrounding it has higher temperature. System is at lower temperature. So heat will flow from surrounding to system. If heat is flowing from surrounding to system, can I say it means system is absorbing heat? Absolutely, system will be absorbing heat. Absolutely, system will be absorbing heat. And do remember, whenever system absorbs heat, Q value as per sign convention is taken to be positive. Whenever system absorbs heat, Q value as per sign convention is taken to be positive, right? And my dear students, one more important thing. For example, if temperature of system is greater than temperature of surroundings, if temperature of system is greater than temperature of surroundings, again there is temperature difference. Again heat will flow from higher temperature to lower temperature. That means heat will be moving from system to surroundings. So at that point of time, I can say system releases heat. I can say system releases heat. And do remember from now onwards, whenever system releases heat, Q value as per sign convention is taken to be negative. As per sign convention, it's taken to be negative. Yeah? These are the two basic things which you have to remember about heat, nothing else. Basic things which you need to remember about heat, nothing else. Heat, it is the mode of transfer of energy, right? Whenever the exchange of energy has to happen between system and surroundings, this exchange of energy can happen via heat. So heat is nothing, it is just the mode of transfer of energy, which flows due to temperature difference, always from higher temperature to lower temperature. Whenever system absorbs heat, Q value positive. Whenever system releases heat, Q value negative. That's all. Yeah? Point number one. At the same time, I have told you in the beginning itself, heat is the example of what? It is the example of path function. Heat is the example of what? It is the example of path function. Something which I already mentioned in the beginning. Yo? I hope this is clear. Moving ahead. There is one more thing that's called as work. Work is represented by W. Work is represented by W. Now the point is, how do we define work? How do we define work? Again, the similar thing, guys. Work is again the mode of. It is again the mode of transfer of energy. Mode of transfer of energy between the system and surroundings. Between the system and surroundings. Work, it is again the mode of transfer of energy between the system and surroundings. Whenever exchange of energy has to happen between system and surroundings, whenever energy has to go outside the system, or whenever energy has to enter into the system, this exchange of energy between system and surroundings, it can happen via work as well. It can happen via heat as well. It can happen via work as well. So work is again what? It is again the mode of transfer of energy between system and surrounding. Yeah? Now there are some very important points which you need to understand. Have a look, guys. Understand this particular thing. For example, this is the container. Let's say this is the container. And this container, over here, you have got a piston. The piston can go out, it can come inside as well. Piston can go out, it can come inside as well. For example, you have got the gas inside the container. This is the ideal gas in the container. So this ideal gas is my system right now. It is my system right now, yeah? When the piston is, for example, at point A, volume of the container is, for example, V1. And you know, an ideal gas occupies the volume of container in which it is kept. So right now, volume of the ideal gas is V1. Right now, volume of the ideal gas is V1. Correct? Yeah? Right now, volume of the ideal gas is V1. Now, guys, try to understand few things. If you analyze this piston over here, right? If you analyze this piston over here, can I say these gas molecules which are present in the container, they'll be colliding with the piston? Absolutely. So in this particular direction, I'll be saying there will be pressure of gas, right? In this direction, there will be pressure of internal gas, right? Pressure of internal gas. Now, my dear students, outside this piston, there is atmosphere. And you know, atmosphere contains gases as well, right? So those gas molecules will be also colliding with the piston from outside. So on this particular side, from this particular side, there will be one more pressure. That's something which you call as P external. So on the piston, how many pressures are there? There are two pressures acting on the piston. There are two pressures acting on the piston. One is P gas due to the internal gas. One is P external due to the atmosphere. Right? Now you tell me one thing. Case number one. My dear students, if P gas is greater than P external, if P gas is greater than P external, you tell me, if P gas is greater than P external, will the piston come inside or will the piston go outside? If P gas is greater, the piston will go outside. And when the piston goes outside, let's say the piston goes outside and finally it stops here at point B. When the piston goes outside from A to B, is the volume of container increasing? Absolutely. The volume of container is increasing. Right? If the volume of container is increasing, we know the ideal gas occupies the volume of container. That means the volume of gas will be increasing as well. Perfect. So can I say, if P gas is greater than P external, can I say V2 will be greater than V1? Final volume of gas will be greater than that of initial volume of the gas. Now, if final volume of the gas is greater than initial volume, does that mean the volume of the gas is increasing? Yes, absolutely. The volume of the gas is increasing. And increase in the volume of the gas is something which we call as expansion. Increase in the volume of the gas is something which we call as expansion. And whenever there is expansion, we always say work is done. Whenever there is expansion, we always say work is done by the system. We always say work is done by the system. Right? Except in case of free expansion. That's something which I'll be teaching you separately. Okay? Whenever there is expansion, we always say work is done by the system. And whenever work is done by the system, W value is taken to be negative as per sign conventions in chemistry. In chemistry. In physics, you take it positive. In physics, you take it positive. This was case number one. This was case number one. Now, let me talk about case number two. Let me talk about case number two. Now, you are going to decide what is going to happen. And keep on telling me in the chats continuously. For example, if P external is greater than P gas, if P external is greater than P gas, the piston will come inside. Volume of the container will decrease. That means volume of the gas is decreasing. So V2 will be less than V1. Decrease in the volume of the gas is something which you call as compression. The gas is undergoing compression. Whenever there is compression, we always say work is done on the gas. We always say work is done on the gas. And whenever work is done on the gas, W value as per sign convention is taken to be positive in chemistry. Is taken to be positive in chemistry. Right? Is this clear? Now you tell me one more thing. Case number 3. If by chance P gas is equal to P external, if P gas and P external both are equal, will the piston move? Will the piston move? The piston is not going to show any movement at all. If the piston is not showing any movement, that means there will be no exchange of energy via work. There will be no exchange of energy via work. There will be no exchange of energy between system and surroundings via work. So W value will be 0. W value will be 0. Right? And my dear students, one more important thing. Talking about this work, as I told you already, work is the example of path function. It depends on initial final state as well as the path followed. Now, till now, what you observed one thing. You observed one thing. Whenever the piston is showing any movement, whether it's going outside or inside, exchange of energy between system and surrounding is happening via work. Except the free expansion, leave that part aside. Right? So whenever basically the piston is showing any sort of movement going outside or inside, work is either done by the system or is done on the system. If there is expansion, work is done by the system, W value negative. If there is compression, work is done on the system, W value positive. Yeah? Now comes the point. The point is, how do you calculate the work? How do you calculate the work? What is the general expression to calculate work? What is the general expression to calculate work? My dear students, I'm not going to derive this expression because derivation is of no use at this point. We'll see the expression, we'll try to use it in questions, nothing else. Yeah? Okay? General expression to calculate work. My dear students, there is one general expression by means of which we can calculate work. It is minus integral initial volume of the gas to final volume of the gas. This is P external multiplied by dV. This is the general expression by means of which you can calculate the work done. This is the general expression by means of which you can calculate the work done. Understand and remember, this is P external here. This is P external here. Okay? Now, in this chapter only, we have to discuss two things basically. In this chapter only, we have to discuss two things. We have to discuss two things. What are those two things? What are those two things? What are those two things? My dear students, later on, I'll be letting you know that we classify processes into two types. Later on, I'll let you know that we classify processes into two types. One is called as a reversible process. One is called as irreversible process. One is reversible, one is irreversible. What are these irreversible? You'll get the idea afterwards, okay? Just remember right now. In case of reversible processes, what you'll observe? We'll observe in reversible processes, P gas will be almost equal to P external. And in case of irreversible processes, what you'll observe? You'll observe external pressure is constant. You'll observe that external pressure will be constant in irreversible process. Now people, if in reversible process P gas is almost equal to P external, that means when I need to calculate work done in reversible process, when I need to calculate work done in reversible process, when I need to calculate work done in reversible process, what is going to be the expression? Minus integral V1 to V2. V1 to V2. Instead of P external, I'll be writing P gas multiplied by dV. This is the general expression which I'll be using to calculate work in case of what? In case of reversible processes. In case of reversible process. I told you in irreversible processes, P external is constant. If P external is constant, take it out of integral. Integral of dV is V, upper limit, lower limit. So you get the final expression. Work done in irreversible processes is equal to minus P external. It's going to be V2 minus V1. Or you can write it as W irreversible is equal to minus P external delta V. This particular expression, which you'll be using here, this particular expression, which you'll be using here, it is valid only for irreversible process, not reversible process. In reversible process, how do we calculate work? This is how you calculate work in reversible processes. This is how you calculate work in reversible process. You have to remember these two expressions for now. I did not derive them because I do not need them. I do not need the derivation. I do not need the derivation. Is this clear? You have to remember them. Their application part you will get to know in some time. Okay, you will get to know how do we solve questions on the basis of them. Okay, let me give you one simple example so that you won't feel bad. Okay, a system means ideal gas. A system undergoes an expansion. A system undergoes an expansion from 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube. System undergoes an expansion from 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube against a constant external pressure. One of the simplest formula-based question. Against a constant external pressure of 1 Newton per meter square, or let's not call it as 1, just a second. against a constant external pressure of 10 raised power 5 Newton per meter square. Calculate work done in joules. Calculate work done in joules. One thing which I would want you guys to analyze at this point. MedTalks is saying lab process is reversible. What do we mean by that? I'm unable to get you. Yeah, lab process equal to reversible? Who has told you lab processes are reversible? I'll be discussing reversible, irreversible in detail. Just wait for that, right? There are a lot of things. It's a very big debate, basically. This reversible, irreversible, it's a very tough thing to understand, actually, right? In book, there is a simple line given related to reversible, irreversible, but actually it's a vast topic. It's a very big, huge topic. A system undergoes an expansion from 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube against a constant external pressure of 10 raised power 5 Newton per meter square. Calculate work. So first of all, try to analyze one thing. Try to understand one thing. It is mentioning that expansion is happening against constant external pressure. Expansion is happening against constant external pressure. When external pressure is constant, the process is supposed to be irreversible. So first of all, the process is irreversible. So we understood the process is irreversible. And in case of irreversible processes, how do we calculate work? In case of irreversible processes, we do not use the integration. So it's going to be minus P external, V2 minus V1. So W irreversible has to be equal to minus P external. P external is 10 raised power 5 Newton per meter square as per SI system. V2 minus V1. V2 is final volume minus initial volume. Minus initial volume, right? Since I have used pressure as per SI system, I have used volume as per SI system. So work, its units will be also there in SI system. Its units will come as per SI system. That means joules. I've used pressure as per SI system. I've used volume as per SI system. So that means the value of W will come as per SI system. That's joules. Agreed? Now tell me one thing. This is going to be 10 raised power 5. Now, if I take 10 raised power minus 3 common, for example, if I take 10 raised power minus 3 common, it's going to be 10 raised power minus 1 divided by 10 raised power minus 3, minus 1, correct? I took 10 raised power minus 3 common. That's all, right? Now, guys, 10 raised power minus 3, 10 raised power 5 makes it 10 raised power 2, correct? 10 raised power 2. 10 raised power minus 3 will go up. It becomes 10 raised power 3. 10 raised power 3 into 10 raised power minus 1 becomes 10 raised power 2. That is 100. 100 minus 1 is 99. So this is the final answer. 99 into 10 raised power 2 joules. This is the work. This is the work. And the sign in the beginning is minus. And this minus sign indicates that it is expansion. Right? Expansion is happening. This minus sign indicates that expansion is happening. Perfect. This is just one simple example. This is a simple example. It's the very basic example which I gave you. So that you can understand how do we use that formula for irreversible. You have to discuss it in detail. Again, I'm telling you, right? Right? I'm just teaching you basic things. Perfecto. Now, guys, try to understand few more things. Just a second. Let me use one slide which will be already made. That's a prepaid slide, right? Sorry, pre-made I have to say. I said prepaid. Wow. Just a second. Since, as I told you, the heat and work, they are the mode of transfer of energy. Do remember the units of energy as well. The SI unit of energy is joule. The SI unit of energy is joule. Number one. Number two, the CGS unit of energy is erg. Right? Heat and work, they are the modes of transfer of energy. Perfect? So, SI unit of energy is joule. CGS unit is erg. 1 joule is 10 raised power 7 erg. The other units of energy which we shall be using in this chapter, they are ATM liter, bar liter or calories. These are the other 3 units which we shall be using in this chapter. ATM liter, bar liter, calories, right? These are the other units of work. Now we have to remember their relationship. Do remember, this is important. 1 ATM liter is equal to 101.3 joules. Something you need to remember. 1 bar liter is equal to 100 joules. Again important. 1 calorie is equal to 4.2 joules and 1 ATM liter is equal to 24.2 calories. This conversion is very, very, very important. So remember it. This conversion is very, very, very important. So remember it, guys. Right? This is the relationship between the different units of energy, which we shall be frequently using in this chapter. Yeah? Now, guys, I'm going to ask you a question. Let me ask you a question. This is not one question, these are 4 questions. These are 4 questions. These are 4 questions. Understand? My dear students, look at the first example. The first example is something like this. 4 times NH3. 4 times NH3 gas plus 7 times O2 gas. It gives what? It gives 4 times NO2 gas plus 6 times H2O gas. Correct? This is the reaction. First of all, as you can see in the reaction, all the reactants and products, they are in gaseous phase. Agreed? They are in complete gaseous phase. They are completely in gaseous phase. Okay? And it's mentioned that all these reactions are happening at STP. That means this particular reaction, it is happening at constant pressure and temperature. It is happening at constant pressure and temperature. Right? As per your ideal gas equation, PV is equal to nRT. Since pressure and temperature is constant, R is already constant. Can I say volume is directly proportional to moles? Absolutely. Volume will be directly proportional to moles. So that means if moles will be increasing, volume will be increasing. If moles will be decreasing, volume will be decreasing. Now look at this particular reaction. Look at this particular reaction. 4 plus 7 makes it 11. So on reactant side, we have got 11 moles. On product side, we have got 10 moles. So when this process is happening, when this reaction is taking place, are the moles increasing or decreasing? The moles are decreasing. If the moles are decreasing, that means the volume will decrease. Decrease in the volume of the system is what we call as compression. And we already know, whenever there is compression, work is done on the system. And whenever work is done on the system, W value, as per sign convention, has to be taken as positive. So in the first process, during the first process, W value is positive. Work is done on the system. Agreed? Agreed? Okay. And this particular concept you'll only use when all the reactants products will be in gaseous state. When all the reactants products will be in gaseous state. And when the reaction will be happening at constant pressure and temperature. This concept you'll use there. Right? The second concept. First concept is done. Second, gas, liquid. Now state has been changed. It's not a homogeneous reaction. State has been changed. It's liquid now. How do we check it now? My dear students, understand one thing. On reactant side, we have got gases. On product side, we have got liquid. On reactant side, we have got gases. On product side, we have got liquid. So, during the process, gas is getting converted into liquid. During the process, gases are getting converted into liquid. Conversion of gas into liquid. That means molecules will be coming closer. Volume of the system will decrease. Decrease in the volume of the system is what you call as compression. Whenever there is compression, work is done on the system. And whenever work is done on the system, W value is taken to be positive. Clear? Clear, guys? Because gases are getting converted into liquid. Yeah? Perfect. All right. One more thing. Solid is getting converted into liquid. Whenever a general question comes, a solid is getting converted into liquid. Solid is getting converted into liquid. It is the case of expansion, right? Volume will be increasing basically, right? And increase in the volume is what we call as expansion. Whenever there's expansion, work is done by the system, W value negative. But this is ice here. Ice is getting converted into liquid water. It is not the general case. It is a particular case. Ice is getting converted into liquid water. My dear students, tell me whether ice has more volume or liquid water has more volume. Ice has got a special cage-like structure. Ice has got a special cage-like structure. due to which its volume is more than that of liquid water. Due to which its volume is more than that of liquid water. So ice will have more volume, liquid water will have less volume. So during the process, is the volume increasing or decreasing? Decreasing. Decrease in the volume, compression. Whenever there's compression, work is done on the system. W value, again positive. Correct? Right? Solid is getting converted into gas. Now it's genuine. It's understood. Solid is getting converted into gas. So this is clear cut the case of expansion. Whenever there is expansion, work is done by the system, W value negative. Perfecto. Is this clear, guys? Quickly in the chats. Is this clear to everyone? Let me know once, quickly. So this was not a single question. These were 4 concepts basically, right? These were 4 concepts. These were 4 concepts basically. I hope you got to know how to use these different concepts to check whether work is done by the system or on the system, right? I can see not everyone has liked the session yet. What is going on? Don't I deserve a like? Yeah. Okay. Perfecto. Just a second. Let's try to understand one more concept. Let's start with heat capacity, which is denoted by C. Let's start with heat capacity, which is denoted by C. Okay? Heat capacity denoted by C. Heat capacity, which is denoted by C. Or should we take a break for 10-15 minutes first? Let's take a break for 15 minutes, okay? Then only we'll discuss the heat capacity and stuff. Okay? Because a lot of people are asking about the break. Okay, I get it. Respect it. So it's 7:50, so 8:10. Let's start again at 8:10. Right? But I would want every one of you to be back. Okay? I would want every one of you to be back. Because now the things are going to be very, very, very interesting. And if you will be having any sort of doubt in between, you can let me know in the lives, in the chats itself. In the recorded session, if you watch the same session recorded, right, you cannot clear your doubts. So I would want all of you to be back exactly at 8:10, right? Till then, whatever you want to do that. I'll see you all at 8:10. Take care. Bye-bye. See you. So guys, can you all see me? Am I again audible, visible to you? Quickly. Yes, the time on screen is, I don't know, right? It's showing 7:42. Maybe I'm taking session from some other country. So am I perfectly audible, visible again? Quickly let me know with the thumbs ups, everyone. Yes, Satya, you can do that. Let me know quickly in the chats with the thumbs ups if all of you again can hear me. If I am audible and visible to every one of you. All right, guys. So till now, we discussed a lot of basic stuff, right? And now it's the time to enter into the thermodynamics properly. Okay? A lot of basic things we discussed, and I hope you remember all these basic things. These are very, very, very important. Like whatever we have discussed till now, all the things are equally important. Understand this chapter in depth. Yeah? Perfect, guys. So let's get going with something called as heat capacity. So what is heat capacity all about? Let me first of all write its definition, then I'll make you understand what exactly it means. Yeah? All right, guys. So heat capacity, which is denoted with C. Heat capacity, which is denoted with C. How do you define it? It is defined as the amount of heat. The amount of heat required. The amount of heat required to raise the temperature of the substance. To raise the temperature of the substance by 1 degree. By 1 degree. What it means, you'll get the idea in some time. Before that, this heat capacity, as I told you already, it is the example of extensive property. It is the example of extensive property. Now let's try to understand what this heat capacity is all about, right? Understand, guys, properly understand. For example, imagine that this is the object. Imagine this is the object, right? My dear students, this object right now is under thermodynamic investigation, for example. So this object is my system. It is my system. For example, I want to increase the temperature of this system. I want to increase the temperature of this system. I want to increase the temperature of this object, right? So what do I need to do? I need to give some heat to this object. I need to supply some heat to this object to increase its temperature. For example, in order to increase the temperature by dT units, let's say in order to increase the temperature by dT units, for example, I have to supply dQ amount of heat. I'm supplying dQ amount of heat to increase the temperature, by dT units, right? Okay. I'm going to write the same thing in the form of a statement. I'll say, in order to increase the temperature by dT units, how much heat is required? How much heat is required? As I told you, in order to increase the temperature by dT units, heat required is dQ. Heat required is dQ. Now, my dear students, use the unitary method. In order to increase the temperature by dT units, dQ amount of heat is required. So, in order to increase the temperature by 1 unit, how much heat is required? It has to be dq upon dt. It has to be dq upon dt. So what is this dq upon dt over here? This is the amount of heat which is required to raise the temperature of the substance by 1 unit. And the amount of heat which is required to raise the temperature of the substance by 1 unit, 1 degree, 1 Kelvin, whatever, right? That's something which you call as heat capacity. So your heat capacity, which is denoted with C, that is equal dq upon dt. This is the amount of heat which is required to raise the temperature of the substance by 1 unit. Okay? Now, people, if I ask you, what should be the possible units of heat capacity? What should be the possible units of heat capacity? It's simple. In the numerator, you have got heat. In the denominator, you have got temperature. So one of the units can be joules per Kelvin. One more unit can be joule per degree centigrade. One more unit can be, take the unit of heat in calories, for example, it's going to be calorie per degree centigrade, calorie per Kelvin. The choice is all yours to select the unit, right? It is just in the numerator, you have to keep the unit of heat. In the denominator, you have to keep the unit of temperature. Okay? Number one. Number two, try to understand what I'm going to say. Let's assume this is the object whose heat capacity is C. This is the object whose heat capacity is C. Now, my dear students, I want to increase the temperature of this object from T1 to T2. I want to increase the temperature of this object from T1 to T2, right? I want to increase the temperature of this substance from T1 to T2. And I am asking you, how much total amount of heat is required? How much total amount of heat is required to raise the temperature of this object from T1 to T2 if its heat capacity is C? How do we do that? See, guys, from this particular equation, I can say dq is equal to C dt. I can say dq is equal to C dt. Perfect. dq is the small amount of heat to raise the temperature by dt units. I want to calculate the total amount of heat. This is small amount. I need to calculate total amount. What do I need to do? I just need to integrate. Just integrate. Over here, you are integrating with respect to temperature, and you are changing the temperature from T1 to T2. You are changing the temperature from T1 to T2. Right? So, my dear students, integral of dq is q is equal to, if c is constant, it comes out, integral of dt is t, upper limit, lower limit, it's going to be c, t2 minus t1, and t2 minus t1 you can represent by delta t. So, what is the significance of this particular equation? What is the significance of this particular equation? Q stands for total heat exchanged between system and surroundings. Q stands for total heat exchanged between system and surroundings. Delta T is the total change in temperature. It is a change in temperature. By supplying Q amount of heat, whatever is the change in temperature, that is delta T, where C is the heat capacity of this object. I hope this is clear. So, for example, I'm giving you a question. Let's say you've got an object. You want to increase its temperature from 5 degree to 50 degree. You have got the object. You want to increase its temperature from 5 degree to 50 degree. Heat capacity is given. How much heat is required? You'll be using this equation. T is given. Temperature difference, delta T, T2 minus T1, right? Simple and basic. So understand this particular thing as well. Remember this particular thing as well. Yeah? Perfect. Now, people, there is one more term. There is one more term. That's called as specific heat capacity. That is called as specific heat capacity. Specific heat capacity is represented by S. And how do we define this specific heat capacity? Let me define it in a very, very simple words. It is defined as heat capacity per unit mass. It is defined as heat capacity per unit mass of the system. Heat capacity per unit mass of the system, right? So specific heat capacity, it is equal to heat capacity per unit mass of the system, right? Now, my dear students, you already know that if you got the relation, you can just let me know the units. Or before talking about the units, you can write it like this as well. What is C? Heat capacity, which is dq upon dt. So it becomes dq upon mdt. It becomes dq upon mdt. Now you can talk about the units of specific heat capacity. It is just, you have to keep one thing in mind, that in the numerator there is heat. So in the numerator you have to write the unit of heat, and in the denominator it's mass as well as temperature, right? So one of the unit, for example, one of the unit is going to be joule per, let's say mass I'm taking in kg and temperature I'm taking in Kelvin, for example. So this can be one of the unit. You can make a lot of other units as well. Yeah, simple and basic. Now, dear students, S is equal to dq upon m dt. So can I say dq will be equal to ms dt? dq is equal to ms dt. Now imagine that this is the object. This is the object whose mass is m, whose specific heat capacity is S, and you want to change its temperature from T1 to T2. For example, you want to increase its temperature from T1 to T2. And I'm asking you to calculate the total amount of heat, required to raise the temperature of this object, whose mass is m, whose specific heat capacity is S, from T1 to T2. What again you'll be doing? Again, you'll be integrating under the limits T1 to T2. So this is going to be Q, this is going to be ms will come outside, integral of dt is t, upper limit, lower limit, so it's going to be ms delta t. This is one more way. This is one more way of calculating the heat absorbed or heat released by the system. This is one more way of calculating the heat absorbed or heat released by the system. Right? First formula is Q is equal to C delta T. If the heat capacity of the object is given, you have to use the relation Q is equal to C delta T. If the specific heat is given, then you have to use the object ms delta T. Right? Now, at the same time, heat capacity is extensive. Whenever an extensive property is expressed per unit mass, what do you call it as? The new property becomes intensive. So specific heat capacity, it is the example of what? It is the example of intensive property. I hope you remember that. I've already discussed that with you. Right? Now, similarly, the third parameter, what is that? That is the molar heat capacity. Molar heat capacity, right? Which is denoted by Cm. Molar heat capacity, which is denoted by Cm. How do you define this molar heat capacity? Again, let's try to define it in a very simplified manner, right? Yeah. My dear students, molar heat capacity is defined as, the heat capacity. It is defined as the heat capacity per unit mole of the substance. Right? Heat capacity per unit mole. How do you write it? Cm, molar heat capacity. It is heat capacity per unit mole. Heat capacity is dq upon dt. So it becomes dq upon n dt. Now, dear students, you can talk about its units as well. Yeah. For example, heat is joules. In the numerator, you have got mole, and temperature, for example, that's Kelvin. So it can be one of the possible units of molar heat capacity. Right? Now look at this particular equation. Cm is equal to dq upon n dt. So can I say dq is equal to ncm dt? dq is equal to ncm dt. Now imagine that you have got a container, and this particular container, for example, it contains n moles of ideal gas. I'm assuming that the molar heat capacity of the ideal gas is Cm. I want to increase the temperature of this ideal gas from T1 to T2. If I ask you how much heat is required to raise the temperature of n moles of ideal gas from T1 to T2, if its molar heat capacity is Cm, how do you do that? You'll be integrating it with respect to temperature, T1 to T2. Integral of dq is q. N comes out, Cm comes out. Integral of dt is t, upper limit, lower limit. So it's T2 minus T1, which comes out be delta T. Right? This is one more way of calculating the heat exchange between system and surroundings. Yeah? Is it clear, guys? Is it clear? There's one more way of calculating the heat exchange between system and surroundings. Like how much heat is absorbed or released by the system. How much heat is absorbed or released by the system. If its temperature is changed by delta T units, right? If the molar heat capacity of the system is Cm. This is the relation which you'll be using. Now tell me one more thing. Heat capacity is extensive. Whenever extensive property is expressed per unit mole, the new property that comes into existence, that's going to be intensive, right? Something which we already discussed. Extensive property expressed per unit mass, per unit mole, or per unit volume. The new property becomes intensive in nature. So my dear students, why I am telling you all these things? All these things, there's a motive for that. Why is that? Have a look. I'm writing the heading as heat exchange. What is meant by heat exchange? That means the amount of heat absorbed or released by the system to change its temperature. Let's say you want to change the temperature of the system. Either you want to increase the temperature or you want to decrease the temperature. If you want to increase the temperature of the system, then heat has to be absorbed by the system. If temperature of the system has to be decreased, then heat has to be released by the system. Now, how do we calculate the amount of heat absorbed or released by the system? How do we calculate the amount of heat absorbed or released by the system? Either to increase its temperature or decrease its temperature. There are many ways to do that. There are many ways to do that. First way. If heat capacity of the system is given, then how do we calculate Q? It is equal to C delta T. If specific heat capacity is given, then Q has to be equal to Ms delta T. And by chance, if molar heat capacity is given, then Q is to be calculated by this result, Ncm delta T. Whenever you are asked to calculate the amount of heat absorbed or released by the system, whenever you are supposed to calculate the amount of heat absorbed or released by the system, you have to use one of the result from these three, depending on what parameter is given. If C is given, use this result. If S is given, use this result. If Cm is given, use this result. Right? Now, people, over here, there are two things. Over here, there are two things. I'll write at constant volume, and here I'm writing at constant pressure. At constant pressure. Molar heat capacity when defined at constant volume. Molar heat capacity per unit mole, when defined at constant volume. At that point of time, you'll be representing it with CV. Molar heat capacity defined at constant pressure. At that point of time, you'll be representing it with Cp. Now, at constant volume, you are not going to write Q. You'll be writing QV. QV will be equal to NCV delta T. And over here, you'll be writing QP. QP will be equal to NCP delta T. These are two very, very, very important results which I would want you guys to remember. Now, let me just tell you the significance of these two results. My dear students, first thing, what is CV? How do you define the CV? What is CV? CV is basically molar heat capacity. Molar heat capacity at constant volume. It is molar heat capacity at constant volume. What about CP? CP is molar heat capacity at constant pressure. At constant pressure. At constant pressure. Now, if you are asked to calculate the heat absorbed or the heat released by the system at constant volume, whenever this kind of question comes, calculate the heat absorbed or heat released by the system at constant volume. Understand, you have to calculate the value of QV. And QV, as per the result, is equal to NCV delta. And whenever you are supposed to calculate the heat absorbed by the system or the heat released by the system at constant pressure, then you have to use this particular result to calculate QP. So two questions can be asked. Calculate the heat absorbed or released by the system at constant pressure. That means QP you have to calculate. Calculate the heat absorbed or released by the system at constant volume. That means QV you have to calculate. One is NCV delta T, one is NCP delta T. I hope this is clear. I hope this is clear. Right? I hope this is clear. Guys, there are few points which I would want you guys to remember directly from now onwards. Right? Let's not go into the details. Let's remember them directly and try to apply them in the questions. Right? Do remember a few important parameters. For a particular gas, Cp value is always greater than Cv. For a particular gas, Cp value is always greater than Cv. What is Cp? Molar heat capacity at constant pressure. Molar heat capacity at constant volume. For a particular gas, its Cp will be always greater than Cv. What is Cp actually? What is Cp actually? How do you define Cp actually? I'm telling you it's molar heat capacity at constant pressure. What does that mean? It is basically the amount of heat required to raise the temperature of 1 mole of the substance by 1 degree, keeping its pressure constant. And my dear students, what is Cv? It is the amount of heat. It is the amount of heat required to raise the temperature of 1 mole of the substance by 1 degree, keeping its volume constant. I hope you are getting the difference between the two. I hope you are getting the difference between the two. I'm telling you for a particular gas, Cp is greater than Cv. For a particular gas, Cp is greater than Cv. Why is that? If I ask you why is that, what should be your logic behind this? Try to understand what I'm going to say. Try to understand what I'm going to say. I just did not want to teach this in so much of detail, but okay, let's go for it. For example, these are two containers. Understand what I'm going to say. Okay, this is important. For example, I've got two containers. Over here, I'm using a movable piston, the piston which can move upwards, downwards. Over here, the piston is non-movable. Non-movable. That means the piston cannot move. It cannot go up or down, right? Let's assume you have got 1 mole of ideal gas here. Let's assume you have got 1 mole of ideal gas here as well. Okay, 1 mole of ideal gas here, 1 mole of ideal gas here as well. Perfect. Try to understand what I'm going to say. You have got 1 mole of ideal gas in both the containers. Now, my dear students, this piston is non-movable. That means volume of this container is not going to change. That means volume of the gas is not going to change. So I'm keeping the volume constant over here. And here, I'm going to keep the pressure constant. I'm not going to let the pressure of the gas to change. And here, I'm not going to let the volume of the gas to change. Here, I'm not going to let the pressure of the gas to change. Here, I'm not going to let the volume of the gas to change. We have got 1 mole of ideal gas in both the containers. Okay. Over here, 1 mole of ideal gas is present at constant pressure. Over here, 1 mole of ideal gas is present at constant volume. For example, I want to increase the temperature of 1 mole of ideal gas by 1 degree. I want to increase the temperature of 1 mole of ideal gas by 1 degree. Provided when I increase the temperature of the gas, volume of the gas should not change. Piston should not move. Let's assume in order to increase the temperature of 1 mole of the ideal gas by 1 degree, keeping its volume constant, let's assume I have to supply 100 joules of heat. Let's say I have to supply 100 joules of heat. For example, 100 joules of heat are enough to increase the temperature of 1 mole of ideal gas by 1 degree at constant volume. And you know the amount of heat required. The amount of heat required to raise the temperature of 1 mole of ideal gas by 1 degree at constant volume. You call that as Cv, right? You call it as Cv. Perfect? Right? Yeah? My dear students, since the piston is not moving at all, when you are supplying this much of heat, this entire heat which you are supplying, it is used to increase the temperature of the gas only. The piston is not moving at all. But when you start to raise the temperature of this gas, when you start to raise the temperature of this gas, when you start to supply heat, what is going to happen? The piston is movable. The piston is movable. My dear students, when you start to supply heat here, to raise the temperature by 1 degree, you want to raise the temperature by 1 degree. So what you'll be doing? You'll be supplying heat. But when you'll be supplying heat, the kinetic energy of molecules will increase. Kinetic energy of molecules will increase. And when the kinetic energy of molecules will increase, what will happen? Collisions in the container will increase. The pressure will start to increase. But do I have to let the pressure to change? I do not have to let the pressure of the gas to change. I do not have to let the pressure of the gas to change. Perfect. So I'm supplying heat basically. I just wanted to increase the temperature of this gas by 1 degree. So I'm supplying heat for that. But what is happening? When I'm supplying heat, the kinetic energy of molecules is increasing. The pressure starts to increase. But I do not have to let the pressure of the gas to increase. So what should happen? What should happen? Since I'm supplying heat, collisions are increasing. So can I say, in order to keep the pressure same, in order to not, if you do not want to increase the pressure of the gas, what should happen? The piston should go up so that molecules will go far and pressure will remain constant. It will remain fixed. So again, I'm repeating the same thing. Just understand what I'm trying to say. You've got 1 mole of ideal gas. You want to increase its temperature by 1 degree. So you're supplying heat. You're supplying heat. Whatever heat you are supplying, due to that, what is happening? Kinetic energy of molecules is increasing, due to which pressure will start to increase. But I do not have to let the pressure of the gas to increase. So what should happen? Piston should go up so that molecules will again go far, due to which the pressure will remain the same. It won't change. It won't increase. So my dear students, the amount of heat which I'm supplying, it is basically divided in 2 parts over here. Some part of heat is used to increase the temperature, and the remaining part of heat is used to take the piston up. If the piston is going up, that means volume of the system is increasing. If the volume of the system is increasing, that means this is the case of expansion. Whenever there is expansion, work is done by the system. So basically, whatever heat you are supplying here, some part of heat is used to increase the temperature, and the remaining part of heat is used for the work so that the pressure remains constant. Perfect. Imagine that you were expecting that you will have to supply 100 joules here also to increase the temperature by 1 degree. But let's imagine that out of 100, 20 joules is used for work so that pressure remains constant. Other 80 joules are used to increase the temperature. Are 80 joules enough to increase the temperature by 1 degree? No. 100 joules are enough to increase the temperature by 1 degree. So can I say from outside only, I won't have to supply 100 only. I'll have to supply 120 joules. So that, for example, 20 joules are used for work and rest 100 joules are used to increase the temperature by 1 degree. And whatever amount of heat you are supplying at constant pressure, that's what you call a CP. So CP and CV, which one is more? For a particular gas, CP value is always more than CV. Because some part of heat supplied during the constant pressure is used for work. Let me write it. I hope this statement is clear to you. Yeah? So let me once know in the chats if it is clear. As I told you, CP for a gas is always greater than CV. Why? Because some amount of heat is used for work to keep the pressure constant. To keep the pressure of the gas constant, fixed. I hope this is clear. Right? I hope this is clear. So CP is always greater than CV. If CP is greater than CV, if I take the difference between the two, CP minus CV, this is more, this is less. So the difference has to be positive. And this is equal to R. CP minus CV is equal to R. And it's valid for 1 mole of ideal gas. It is valid for 1 mole of ideal gas. CP minus CV is R. And here I'm defining a term, gamma, which stands for Poisson's ratio. Poisson's ratio. It is equal to CP divided by CV. Gamma is equal to CP divided by CV. We got to know CP is greater than CV. So CP divided by CV, its value has to be greater than 1. So gamma value will be greater than 1. For 1 mole of ideal gas, Cp minus Cv is R. For 2 moles of ideal gas, Cp minus Cv will be 2R. For n moles of ideal gas, Cp minus Cv will be Nr. Cp minus Cv will be Nr, right? There is one more result which you need to remember directly. There is derivation as well, but I'm not deriving it. It's of no use for us, right? Do remember Cv is equal to R divided by gamma minus 1. This is one more result, which we'll use frequently in this chapter, right? These are few results which I would want all of you to remember from now onwards. These are all very, very, very important results. These are all very, very, very important results. Okay? And my dear students, there is a particular table which I'm going to give you, and you have to remember the values as well. So over here, I'm mentioning Cv. Over here, I'm mentioning Cp. And over here, I'm mentioning gamma, which is Cp divided by Cv. Now, imagine that you have got a monoatomic gas. Imagine that you have got a monoatomic gas, like helium. Like helium, it is monoatomic. Do remember, Cv for monoatomic gases, it's always equal to 3 by 2R. Pp for monoatomic gases, it's always equal to 5 by 2R. And gamma value, which is Cp by Cv, this divided by this. So it comes out to be 5 by 3. 5 by 3 is just 1.66, right? Now, for example, you will be having a diatomic gas. Diatomic gas, like O2. Or for example, you have got triatomic linear gas. Let's say you have got triatomic linear gas. For example, carbon dioxide. Carbon dioxide is triatomic and at the same time it's linear as well, right? Its Cv is going to be 5 by 2R, Cp is going to be 7 by 2R, and its gamma is going to be Cp by Cv. So it comes out to be 7 by 5, which is 1 point, right? Similarly, if you will be having a triatomic non-linear gas, like SO2, it is triatomic and at the same time it's bent. It's not linear. It's Cv. Okay, or I'll write polyatomic gases. Or polyatomic gases. Their Cv will be equal to 3R. This is equal to 4R. And this will be equal to 4 by 3. The value comes out to be 1.33. Okay. This is the table which you have to remember because we are going to use these values frequently in this chapter. Okay. Tell me one thing. First gas was monoatomic. The second is diatomic, triatomic. So as you go from top to bottom, what is happening to the atomicity? What is happening to the atomicity? This is monoatomic, atomicity 1, diatomic, atomicity 2, triatomic, atomicity 3. So on moving from top to the bottom, atomicity is increasing. And as the atomicity is in a value, it tries to decrease, right? So do remember this particular point as well. This is again important. I hope this is super clear to you. Now, my dear students, before doing the questions, before talking about the actual stuff, there are a few more things. What is that? See, I'm writing Cv for a mixture of non-reacting gases. All these concepts I'll be using in the question. Cv for a mixture of non-reacting gas. Cv for a mixture of non-reacting gas. So for example, imagine this is a container. And this container contains two gases, gas 1 and gas 2. It contains two gases, gas 1 and gas 2. By chance, these gases are chemically non-reacting gases. These are chemically non-reacting gases. So can I say I have got a gaseous mixture containing chemically non-reacting gases? Absolutely. Let's assume molar heat capacity at constant volume for gas 1 is Cv1. For gas 2, it is Cv2. Let's assume molar heat capacity at constant pressure for gas 1 is Cp1. And over here it's Cp2. Let's assume moles of gas 1 in the container are N1. Moles of gas 2 in the container N2. Now, my dear students, if you have to define Cv for the mixture, Cv for the gaseous mixture, there is a simple result which you'll be using. N1 Cv1 plus N2 Cv2 plus N3 Cv3 plus dash 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 divided by N1 plus N2. Divided by N1 plus N2 plus dash. This is the result by means of which we can calculate molar heat capacity at constant volume for a mixture of chemically non-reacting gases. Similarly, if you are supposed to calculate Cp for the mixture, Cp for the gaseous mixture, it's going to be equal to N1Cp1 plus N2Cp2 plus N3Cp3 divided by N1 plus N2 plus dash dash. This is the formula by means of which we can calculate the molar heat capacity at constant pressure for a mixture of gas. Yeah. And dear students, already you know Cp minus Cv is R. So Cp mixture minus Cv mixture, that has to be equal to R. Right? If I ask you, what about the value of gamma for the mixture? The value of gamma for the mixture has to be equal to Cp mixture divided by Cv mixture. Cp mixture divided by Cv mixture. These are some very, very, very important results which you have to remember. And all these results I'll be utilizing in the questions afterwards. Okay? Yeah? And now guys, if all these things are clear, now it is the time to discuss one of the most important topics of the chapter. That is what you call as internal energy. Internal energy. So till now, I use the term internal energy many a times, right? Okay. And I used to tell you we have to discuss this in detail. Now it is the time to discuss the internal energy in detail. Internal energy, it is represented by U, or you can represent it by E. So understand logically what this internal energy is all about. How do you define the internal energy? My dear students, in simpler words, I can say internal energy, it is basically the sum of kinetic and potential energy present in the system. Internal energy is actually the sum of kinetic and potential energy present in the system. The total kinetic energy and the total potential energy present in the system, that gives you the internal energy. For example, what does that mean? For example, let's say this is the container. Okay? Let's assume in this container we have got a real gas. There's a real gas in the container, right? These are the real gas molecules. Now, my dear students, if I ask you, let's assume that the container is at rest. Right? This is something which I'm assuming. Now you tell me, these real gas molecules, whether they'll be in motion or they'll be at rest. These real gas molecules, they'll be in constant random motion. They'll be showing translational motion, rotational motion, vibrational motion, etc. And due to motion, which energy arise? Right? Due to motion, which energy arise? It's kinetic energy, right? So can I say these molecules, they'll be in random motion, due to which I can say these molecules will have kinetic energy. It can be translational kinetic energy, rotational kinetic energy, right? Anything. And apart from that, since it's a real gas, between the real gas molecules, there will be interactions. There are interactions between real gas molecules. And due to interactions, which energy comes into play? Due to interactions, potential energy comes into play. So if it is the real gas, due to motion, kinetic energy will come into play. Due to interactions, potential energy will come into play. If you will take the sum of all the kinetic energies and all the potential energy present in the system, you'll be getting the value of internal energy of the system. In short, you are getting the total energy of the system. Which is the sum of total kinetic and total potential. Kinetic is due to motion and potential is due to interaction. So this is how you define internal energy for a real gas. Now, for the ideal gas, just tell me one thing. If this was the ideal gas, will there be any interactions? Between the ideal gas molecules, there are no interactions. If there are no interactions, what will be the value of this potential energy for the ideal gas? It will be zero. Potential energy comes into play due to interactions. If in ideal gas there are no interactions, so PE value will be 0. So U is equal to total kinetic energy for the ideal gas. For the ideal gas. Perfect. Perfect. Right? For the ideal gas, internal energy is basically the sum of all the kinetic energies present in the system. For the real gas, it is the sum of all kinetic energies and potential energies present in the system. I hope you're getting it. Point number 1. Point number 2. If I talk about internal energy now, if I want to define the internal energy, if I want to write the definition of internal energy, how do I write it? Internal energy is basically the sum total of all the possible kinds of energies present in the system. And the system has to be at rest. The container has to be at the rest in which the gas is present. Okay? Now, people, you tell me one thing. Whether this internal energy is going to be a extensive or intensive property. What is internal energy basically? The total energy in the system. If you change the amount of substance, if you increase or decrease the molecules of gas in the container, the total energy automatically will change. That means internal energy is changing. So internal energy, it is the example of what? Extensive property. Its value changes on changing the amount of substance present in the container, amount of substance present in the system. Now the same internal energy, it is a state function as well. Its value only depends on initial and final state. It is path independent. If internal energy is a state function, you'll be calculating its change, and change in the value of internal energy is equal to U final minus U initial. Okay? Now you tell me one more thing. For a cyclic process, change in internal energy has to be 0, because we know for a cyclic process, change in the value of a state function is always 0. Change in the value of state function for a cyclic process is always 0. Yeah? Okay. One more thing. Internal energy, it is the function of volume and temperature. Internal energy depends on 2 parameters. Internal energy of the gas, it depends on volume as well as temperature. But for a real gas, for an ideal gas, internal energy only depends on temperature. For an ideal gas, internal energy only depends on temperature. It only depends on temperature. Now, my dear students, here I have to teach you a bit of mathematics so that you can understand this internal energy in detail. Understand what I'm exactly going to do. Whenever you write y is equal to f of x, what does it mean? It means that y depends on x. X is the independent variable, y is the dependent variable. If you change the value of x, the value of y will automatically change. If you change the value of x, the value of y will automatically change. And that change in the value of y due to the change in x, that is represented by dy by dx. Change in the value of y due to change in x, that is represented by dy by dx. Correct? Now, my dear students, just try to understand what I'm going to say. For example, you have got a function in this format. Let's say I'm writing z is equal to f of x comma y. Z is equal to f of x comma y. What does it mean? It means that z depends on 2 variables. It depends on x as well as y. So if you change x, z will change. If you change y, z will change. Z is depending on 2 variables. So if you change x, z will change. If you change y, z will change. Correct? So if I want to calculate the total change in z, how do I do that? Over here, I'm not going to use the normal differentiation which you do. Over here, I'll be using the partial differentiation. And try to understand what I'm going to say. My dear students, I'll be writing, what I'll be doing, I'll try to keep y constant. First, I'll try to keep y constant. I'll try to change x. If x changes, there will be change in z. So that change in z due to change in x, I'll calculate, right? How do I represent it? Change in z due to change in x. Keeping what constant? Keeping y constant. So first of all, my first step is I kept y constant. I changed x. And I saw the change in the value of z due to change in x, keeping y constant. So from here, I can get the dz value. Dz is going to be equal to dou z upon dou x at constant y multiplied by this dx. This was my first step. Now look at my second step. Now I'm going to keep x constant. Now I'm going to keep x constant and change the value of y. And when y changes, z will automatically change. I'm going to keep x constant. We'll try to change y. And on changing y, z will change. And then I'll try to calculate change in the value of z due to change in y. How do I represent it? Change in z due to change in y, keeping what constant? Keeping x constant. And from here, I can get the value of dz. Dz is going to be equal to dou z upon dou y, keeping x constant, multiplied by dy. I got two things. Change in z due to change in x, keeping y constant. Change in z due to change in y, keeping x constant. So if I want to calculate the total change in z, that means I have to take the sum of these two. So the total change in z is going to be dou z upon dou x, keeping y constant, multiplied by dx, plus dou z upon dou y, keeping x constant, multiplied by dy. Right? So this equation gives me the total change in z. Right? Change in z due to change in x, keeping y constant, and change in z due to change in y, keeping x constant. Take the sum of both, you'll be getting the total change in y. Total change in z. I hope you got this. Did you get this? Say yes or no in the chats once, then only I can move ahead. Did you get this? Did you get this quickly? Yeah? Okay, do you know why did I do this? Do you know why did I do all this stuff? There is a reason for that. There is a reason for that, my dear students. Try to understand what I'm going to say. I told you for a real gas, internal energy is the function of volume and temperature. For a real gas, internal energy is the function of volume and temperature. So internal energy depends on two variables, volume as well as temperature. So if I want to calculate the total change in internal energy, what will be the total change in internal energy, which I'm representing by du? First, it's going to be change in internal energy due to change in volume, keeping what constant? Keeping temperature constant, multiplied by dV, right? And then I'm going to write change in internal energy due to change in temperature, keeping what constant? Volume constant, multiplied by dt, right? And I hope you now know exactly how this equation comes. I hope you exactly know how this particular equation comes. Okay, so this particular equation, it gives me the total internal energy change, right? It gives me the total internal energy change. But this is the equation for which gas? Real gas. I don't have to talk in terms of real gas. I have to talk only about the ideal gas, right? So what exactly I'll be doing? For an ideal gas, if I want to write the same equation for an ideal gas, how do I write it? See, in this particular equation, you have got two terms. Can you let me know which term will be zero for ideal gas? Which term will be zero for an ideal gas? Ideal gas internal energy only depends on temperature. It does not depend on volume. Ideal gas internal energy, it depends only on temperature. It does not depend on volume. So change in internal energy due to change in volume for the ideal gas, that has to be zero, right? If you change the volume of the ideal gas, will its internal energy change? Its internal energy won't change. So this particular term for the ideal gas, it has to be zero. That means for the ideal gas, du will be equal to dou U upon dou T at constant volume multiplied by dt. And this particular equation, it's actually valid for 1 mole of ideal gas. It's actually valid for 1 mole of ideal gas. And my dear students, this particular term, change in internal energy due to change in temperature, keeping volume constant. Change in internal energy due to change in temperature, keeping volume constant. It is actually called as CV. So du comes out to be CV dt. And this equation is valid for 1 mole of ideal gas. If you'll be having 2 moles of ideal gas, it's going to be 2 times CV dt. 3 moles, 3 times CV dt. N moles of ideal gas, it's going to be du is equal to NCV dt. du is equal to NCV dt. Tell me the significance of this particular equation. Tell me the significance of this particular equation. For example, you have got N moles of ideal gas in the container. You have got N moles of ideal gas in the container. You are changing the temperature of the ideal gas by small dt. By small dt. If you are changing the temperature of ideal gas, definitely its internal energy will change. How much? du. du is the small change in internal energy due to small change in temperature of N moles of ideal gas whose molar heat capacity at constant volume is CV. Correct? Right? So you got to know du is equal to NCV dt. Try to understand one important thing now. Try to understand one important thing. Imagine that you have got ideal gas. Imagine that you have got ideal gas in the container. For example, this is the container. It contains N moles of ideal gas. N moles of ideal gas. Molar heat capacity of ideal gas is CV. Now you want to change the temperature of the ideal gas from T1 to T2. If you are changing the temperature of the ideal gas, definitely its internal energy will change. And I'm asking you to calculate that change in internal energy. How you are going to do that? You are simply going to integrate. With respect to temperature you are changing from T1 to T2. Integral of du has to be delta U. So delta U is equal to integral T1 to T2. It's going to be N CV and it's going to be dt. So this is the general result by means of which you can calculate the internal energy change of the ideal gas when you'll be changing its temperature from T1 to T2. From T1 to T2. Now, dear students, this is first of all important equation. Now, for example, if CV was temperature independent, if CV does not depend on temperature, if CV is constant, take CV out, N already out, so delta U will be equal to N CV. Integral of dt is T, upper limit, lower limit, so it's T2 minus T1. T2 minus T1, right? Or you can write it like this, delta U is equal to N CV delta T. So this particular equation is used when CV for the gas is temperature independent. Temperature independent CV, temperature dependent CV, right? If in the equation they mention that CV depends on temperature, then how do you calculate delta U? Through this result, right? Perfect. And if they say that CV is constant, then this particular result you'll be using. I hope this is clear. Now we will try to understand one more thing. Try to understand one more. See guys, imagine that you have got an ideal gas. For an ideal gas undergoing isothermal process. For an ideal gas undergoing isothermal process. What does that mean? That means you are changing the state of the gas. You are changing the state of the gas without changing its temperature, right? So temperature of the gas is kept constant. If temperature is constant, delta T has to be 0. If delta T is 0, that means delta U has to be 0. So do remember that particular ideal gas, right? When the ideal gas undergoes isothermal process, its delta U has to be 0. Its delta U has to be 0. But this is particularly valid for ideal gas, right? One more thing. I told you delta U is equal to NCV delta T, correct? Right? Now, my dear students, it's evident. If delta U is positive, that means T2 minus T1 should be positive. T2 minus T1, when it's going to be positive? I'm telling you something like this. If delta U for the ideal gas comes out to be positive, what does that mean? That means U2 minus U1 is coming out to be positive for the gas. So what does that mean? That means U2 is greater than U1. What does that mean? That means the internal energy of the gas is increasing. That means the internal energy of the gas is increasing. If delta U is positive, that means the gas's internal energy is increasing. Now simple, right? If delta U is positive, that means T2 minus T1 has to be positive. So T2 has to be greater than T1. So it clearly tells you T2 has to be greater than T1. Perfect. So what does this mean? This means that on increasing the temperature of the gas, internal energy of the gas increases. Right? On increasing the temperature of the gas, internal energy of the gas increases. So you can categorically say U is directly proportional to T. Internal energy is directly proportional to temperature. And it's evident also, when you increase the temperature, what will happen? The internal energy, the total energy present in the system, that will increase. As simple as that. Right? Now, my dear students, one simple thing if I ask you, please see if you can solve this one or not. One simple thing I'm asking. One simple thing. For example, I'm giving you a graph. Or let's not go to the graph yet. Let's try to understand one. Few minutes back, I told you du is equal to ncv dt. Correct? du is equal to ncv dt. For 1 mole of ideal gas. Let's say du will be equal to cv dt. Absolutely. So can you calculate cv from here? It's going to be du upon dt. cv is equal to du upon dt. What is the meaning of this du upon dt? It gives you the slope of tangent. It gives you the slope of tangent at a point. Slope of tangent at a point on internal energy versus temperature curve. It gives you the slope of tangent at a point on internal energy versus temperature curve. Now, my dear students, you can say more the slope, more the CV. For example, I'm giving you a question like this. Let's say this is the graph. For example, hypothetical question. Internal energy versus temperature for 1 mole of gas, or 1 mole of ideal gas. The graph is, for example, like this. And for example, what exactly I'm doing, I'm selecting 2 points. This is point A and this is point B. I'm asking you at which point CV value is more. Is CV at A more than that of CV at B, or less than that of CV at B, or equal to that of CV at B? What do you think? What exactly you'll be doing? You'll be extending this line. You'll be drawing a tangent here. You'll be drawing one more tangent here. Correct? Now measure the angle. This is theta A and this is theta B. Now you are going to tell me which theta is more. Theta A is more than that of theta B. So can I say tan of theta A will be also greater than that of tan of theta B? Absolutely. So can I say slope at A is greater than that of slope at B? And wherever slope is more, CV value has to be more. So CV at A will be greater than that of CV at B. If this is clear, let me know in the chats quickly. Every one of you. This was all about your internal energy, my dear students. Quickly, everyone. Everyone in the chats. Is this clear? Okay, if this is clear, can you solve one simple question if I give you? Just try to solve this question. Let me see if you can solve this one or not. The question is, just wait a second. Before doing the question, few minutes back, we discussed one thing. We discussed how to calculate QV. QV was equal to NCV delta T. And few minutes back, you saw one more thing. NCV delta T is basically the value of delta U for the ideal gas. NCV delta T is basically the value of delta U for the ideal gas. So take a note of one important thing. Take a note of one important thing. What is QV? QV is basically heat absorbed or released by the system. Heat absorbed or released by the system at constant volume. At constant volume is always equal to internal energy change. So question can be asked in two ways. My dear students, either they'll ask you directly calculate the internal energy change delta U, NCV delta T, or they can ask you calculate the heat absorbed or heat released by the system at constant volume. Whenever they ask you calculate the heat absorbed or released by the gas at constant volume, understand you have to calculate delta U only. And delta U is nothing, that's NCV delta T for the ideal gas. Okay, so do remember this particular thing as well. Do remember this particular thing as well. So question can be asked in two ways. Either they'll ask directly the value of delta U, or they can ask you calculate the heat absorbed or released by the gas at constant volume. Okay. Now, if I give you one question like this, calculate delta U in joules. Calculate delta U in joules. When 10 decimeter cube of helium gas at STP is heated to 100 degrees centigrade, assuming ideal gas conditions. Assuming ideal gas conditions. Can you give it a try? Can you give this question a try? Can you solve it? Can you give it a try? See guys, how to solve this. As far as the question is concerned, you have got 10 decimeter cube of gas. 10 decimeter cube means 10 liters because 1 decimeter cube is equal to 1 liter. So 10 decimeter cube of helium gas you have. Helium gas you have. Where at STP. At STP. That means the temperature of the gas is 0 degrees centigrade. The pressure of the gas is equal to 1 atm. So we have got a gas. Basically, we have got a gas whose volume is 10 decimeter cube, whose temperature is 0 degrees centigrade, pressure is 1 atm. Now, what exactly you are doing? You are changing the temperature of the gas from 0 degree till 100 degree. Till 100 degrees centigrade. Since you are changing the temperature of the ideal gas, on changing the temperature, what is going to happen? On changing the temperature, internal energy will change. Since you are increasing the temperature, so internal energy will increase. And we have to calculate that change in internal energy. We have to calculate that change in internal energy. So delta U we have to calculate. Delta U we have to calculate. My dear students, how do we calculate delta U? First of all, try to understand whether it's mentioned in the question that CV is temperature dependent. It's not mentioned anywhere. CV is temperature dependent. It's not mentioned, right? So you'll be taking the value of CV as constant. You'll be taking the value of CV as constant. And when CV is constant, delta U has to be equal to NCV delta T. NCV delta T means NCV T2 minus T1. NCV T2 minus T1. So delta U will be equal. N stands for number of moles of gas. You had 10 liters of gas at STP. 10 liters of gas at STP means how many moles? Givenly volume divided by 22.4. So these many moles we have. CV for helium. Helium is monoatomic. For monoatomic, CV is 3 by 2R. 3 by 2R. T2 minus T1. T2 minus T1. T2 is T2 minus T1. The difference of the temperature is going to come as 100. Now you have to get the answer in joules. If you have to get the answer in joules, which value of R you'll be using? If you need to get the value of delta U in joules, you'll be using the value of R as 8.314 and multiplied by 100. You need to solve this particular term and get the answer of delta U, particularly in joules. That's how you solve it. I hope this is clear. Let me know once in the chats if it's clear, people, quickly. Is this clear to everyone? Is this clear to everyone? Quickly in the chats. Guys, thermodynamics cannot be done in one shot. I don't know the thumbnail is wrong. It's not one shot. It will be done in 2 sessions. One is today's session. Another session will happen on Saturday, day after tomorrow at 5 p.m. Okay? Because it's a huge chapter. No way it's going to complete it like one session. I mean, it can be completed if the session duration was 10 hours. Okay, is it clear to you? All right, guys. So try to understand one more thing. Try to understand one more thing. There is something called as first law of thermodynamics. There is something called as first law of thermodynamics. First law of thermodynamics. What this first law of thermodynamics is all about? First thing, it is the energy conservation principle. It is the energy conservation principle. It is the energy conservation principle. Point number 1. Point number 2. Point number 2. When the state of the system changes, when the state of the system changes, there will be change in its internal energy. There will be change in its internal energy, which can be brought about, guys, can you write it? I'll dictate. Which can be brought about in 2 ways. Which can be brought about in 2 ways. Number 1, when heat is absorbed or released by the system. When heat is absorbed or released by the system. Number 2, when work is done by or on the system. When work is done by or on the system. What does it mean? Let's try to decode all these things, right? Let's try to decode all these things mathematically. And mathematical interpretation is just important. Nothing else with the definitions and stuff. Okay? See guys, try to understand now properly what I'm going to say. For example, this is the container. For example, this is the container. And this container, let's imagine that it contains an ideal gas. It contains an ideal gas. This is the piston fitted at the top, right? Let's assume the gas is right now present at its initial state. Let's assume that the gas is present at its initial state. Let's assume that the total energy present in the system right now is U1. U1 stands for total energy present in the system. Yeah? Total energy present in the system, which is called as internal. So internal energy, when the system is present at initial state, is U1. Now, what exactly we will be doing? For example, I am supplying Q amount of heat to this gas. For example, I'm supplying Q amount of heat to this gas. For example, I'm supplying Q amount of heat to this gas. My dear students, when you supply Q amount of heat to this gas, can you tell me what will be the total energy possessed by the gas now? Initially, the total energy of the gas was U1. Now it's going to be U1 plus Q. This is the total energy possessed by the gas. This is the total energy possessed by the gas. Correct? For example, let's assume that W amount of work is done on the system. And when W amount of work is done on the system, what will happen? Let's assume W amount of work is now done on the system. So let me tell you, whatever work was done on the system, whatever work was done on the system, let's assume that entire work is stored in the gas in the form of its internal energy. Initially, you had the gas whose internal energy was U1. Now you supplied Q amount of heat. Now its internal energy, total energy is U1 plus Q. Now I'm bringing the piston down. That means compression is happening. Work is done on the system. And whatever work is done on the system, that work is stored in the gas in the form of its internal energy. So can you tell me now what will be the total internal energy of the gas? It has to be U1 plus Q, and W amount of work was done on the gas. Right? I'm assuming this is the final state of the gas. I'm assuming this is the final state of the gas. So this whole term, it has to be the final internal energy of the gas. Right? If I take U1 on that side, so it's going to be U2 minus U1. U2 minus U1 is nothing, that's delta U. So delta U has to be equal to Q plus W. This is the mathematical formulation of your first law of thermodynamics, which you have to remember. This is your mathematical formulation of first law of thermodynamics, which you have to remember. Be careful with one thing. Whenever heat is absorbed by the system, you have to take the value of Q as positive. Whenever heat is released by the system, you have to take the value of Q as negative. You have to take the value of Q as negative. Right? Let's exactly see what kind of questions are asked. Let's exactly see. Right now, only basic questions will be asked. Okay? Because we have just derived this relation. Okay? When we check the thermodynamic processes, there it becomes good. Right now, only basic questions will be there. For example, again, I'm telling you, be careful with these terminologies. Be careful with these terminologies. Be careful with the sign conventions. When heat is absorbed, Q value positive. Heat is released, Q value negative. Right? This is the first question on the screen. Based on first law of thermodynamics, a very simple basic question. Let's try to solve this. The question is, a system expands from 5 liter to 10 liter. A system expands from, system means ideal gas. So ideal gas is showing expansion from 5 liters to 10 liters. So I would say initial volume of the gas is 5 liters. Final volume of the ideal gas, that is 10 liters. Correct? The gas is showing expansion against a constant external pressure. Against a constant external pressure of 2 atm. Right? The gas is showing expansion against the constant external pressure of 2 atm. Right? See, you already know it. For example, this is the container, this is the piston, right? This is the gas inside. Perfect. This is pressure of gas, and this is external pressure. If there is expansion, that means the piston is going out. Piston is going out. Expansion is happening. Work is done by the system. Work is done by the system against what? Against this external pressure, right? So it's mentioned that the system is expanding from 5 liters to 10 liters against a constant external pressure of 280. If it absorbs 800 joules of heat, during the expansion, system is absorbing 800 joules of heat. And when heat is absorbed by the system, Q value is taken to be positive. So it's plus 800 joules. Calculate the value of delta U in joules. Calculate the internal energy change during the process. Calculate the internal energy change during the process. Delta U you have to calculate. Can you give it a try? It's simple. First of all, it's mentioned that during the expansion is happening against constant external pressure. Now you tell me, if external pressure is constant, should the process be reversible or irreversible? You tell me that. Tell me in the chats quickly. Should the process be reversible or irreversible? Quickly. Should the process be reversible and irreversible? If external pressure is constant, I have told you in the beginning, when I discussed work, it has to be irreversible because external pressure is constant, right? So, how to calculate delta U? What is delta U all about? It's Q plus W as per first law of thermodynamics, correct? Since the process is irreversible, so I'm writing W irreversible. Yeah, simple. I need to calculate delta U in joules. That means Q has to be in joules and W at the same time has to be in joules as well. Well, Q is already given in joules, right? W irreversible. How do you calculate W irreversible? We have discussed it. It's minus P external delta V, which is V2 minus V1. So dear students, minus P external is how much? 2 atm. V2 minus V1. Final volume minus initial volume. So 10 minus 5 is 5. So pressure is an atm volume in liters. So its units are supposed to be in atm liter. Pressure volume, atm liter, right? So it's going to be minus 10 atm liter. But my dear students, whether I need to take W in atm liters? No, I have to take W in joules. So minus 10. 1 atm liter is 101.3 joules. The value comes out to be minus 1013 joules. This is the value of W. This is the value of W, right? This minus signifies that expansion is happening. So I was supposed to calculate delta U is equal to Q value is 800 joules plus W is minus 1013 joules. So the final value will come out to be minus 213 joules. So this is the value of delta U which you are supposed to calculate. Is this clear? Is this clear, guys? All the things were mentioned, right? And we solved it. Done, guys? Clear? There is one more question, right? There is one more question. Okay. Can you give this a try? Let me write it as 0.5 atm. Can you give it a try quickly? Can you give it a try? So this is your homework question. Do let me know its answer in the comment section of this particular video, right? And I think this much is enough for today. I'm tired, right? I'll see you day after tomorrow with the part 2. Yes, Muntazir, it's enough. That's why I'm teaching, bro. The rest part of the thermodynamics I'll be doing on Saturday, okay? Perfect. So all the things which I discussed till now, whether all the things are clear till now or not, can you let me know? Whatever things we have discussed, are these things clear? Are these things clear? Whatever I have discussed, and please take a note of every single thing. Take a note of every single thing, okay? Yeah? And guys, the question which I gave you, do give it a try. Do let me know its answer in the comment section, and I would want everyone to write its answer. Everyone means everyone, okay? So day after tomorrow, on Saturday, 5 p.m., we'll have the part 2 of thermodynamics, okay? So, chalo, with this, I'll be taking a leave. I'll see you day after tomorrow, okay? Have fun. Take care. God bless you all. See you on Saturday, 5 p.m. Bye-bye, guys.